Dr. Kondareddy?
Good morning, sir.
Good morning. This is Khandekar here. I'm just checking whether everything is okay.
Yes, sir. It is everything fine, sir.
Okay, so I will be off and on, and then I'm doing other things.
Okay,
So
sir.
then we will sort of continue at 10:30. Yeah.
Sure, sir.
Okay. Thank you.
Thank you, sir.
So what time you are starting right now?
9 o'clock, sir.
Nine. Okay. Perfect. Thank you.
One and all. I welcome Dr. Srikanth for the as a speaker of session 4. I am very happy to introduce session 4 speaker, Dr. Srikanth Rangarajan. Dr. Srikanth Rangarajan is currently a research professor in the Department of Mechanical Engineering at the State University of New York, Binghamton, New York, USA. He took his BE in Mechanical Engineering 2007 to 2011 from Sri Sai Ram Engineering College, which is affiliated to Anna University. He began his career as graduate engineering trainee at WABCO India 2011 to 2012. He joined the master's program MS in thermal engineering at IIT Madras in 2012. He then upgraded to doctoral studies at IIT Madras in 2013 in the area of heat transfer, especially in the thermal management and optimization of phase change material based heat sinks under the guidance of Professor C. Balaji. Dr. Srikanth Rangarajan is the inventor of the rotatable heat sink, a recent patent awarded by the Government of India. He has 12 papers published in international journals. He has also presented 6 papers in international conferences. He has authored one book titled Phase Change Material Based Heat Sinks, a multi-objective perspective. His recent research work includes liquid cooling in data centers, three-dimensional integrated circuits, and associated optimization. Now I request Dr. Srikanth Rangarajan to present this session.
Thank you so much, Dr. Kondareddy, for the nice introduction. And thank you, everyone, for being present to this lecture. I just share my screen.
Yeah.
So you're able to see my screen?
Yes.
Okay. Thank you so much, Dr. Kondareddy, for this opportunity to present. And good morning, everyone. I'm Srikanth Rangarajan, and today I'm going to talk on the optimization opportunities that I think is available in the data center thermal management. So before I even start my presentation, I think it's a globally tough situation because of the pandemic, and I really hope every one of you here are staying safe and are doing well. So continue to stay safe, and thank you. So my presentation outline is going to be on 3 of these categories. One is going to be on the data center cooling, and the second one is going to be on optimization, and my third one would be on advanced technologies. So in each of these categories, I would be talking about what is data center cooling or what is optimization, and why do we need to cool a data center, or why do we want to optimize a data center, and how to cool data centers, and also how to optimize. So on each of my slide, I would like to identify and then outline some of the opportunities that we have with regard to optimization in the data center cooling. So When we talk about the thermal management of heat sinks, I think it's a well-known topic in the field of heat transfer. So we see this kind of schematic mostly when it's concerning to a data center. So we have this active device that is called as the cores or the multi-chip modules, over which we have this heat sink. And in between the heat sink and the active device, we have a lot. We have like more than 3 to 4 sequential conduction layers. And this TIM is abbreviated as the thermal interface material. And this IHS abbreviates as integrated heat spreader or the lid. And as we all know from the Newton's law of cooling, that the heat generated from the chip is the heat transfer coefficient times the area of the chip multiplied by the temperature difference between the chip and the incoming fluid. Now, if you look at these components here, like the heat transfer coefficient and the inlet temperature of fluid, to control both of these, it requires energy, which means it requires work. And this H, the heat transfer coefficient, depends on the cooling technology, which means it could either be an air cooling or a liquid cooling, basically the choice of the fluid, and the microchannel design. And this T inlet, the incoming fluid's temperature, requires a chiller plant or a refrigeration plant for it to operate, or even a heater thing to operate to control the temperature. And this area of the chip and the temperature of the chip are the two components which are often posed as a constraint in the optimization problems, right? Like the chip area that's available to you, or the footprint area for you to install the heat sink available to you, are often fixed and remain constant. And the T chip is something that is posed as a constraint, and violating the constraint of the T chip would result in a penalty. Now, the Q chip depends on the number of transistors that we are packing in this red zone, which is the active device. So it's predominantly covered by the Moore's law, which I would come in the next slide. So what do we desire actually is like the minimum area. So we desire minimum area, and we desire minimum chip temperature. We desire maximum heat transfer coefficient with minimum work. And also we want to achieve the maximum Q, right? We want to remove the maximum heat by kind of minimizing and maximizing all these components. So how complicated is the problem? Is that once you have this non-uniform chip temperature with localized hotspots arising in this red zone, that is the active device, I think the problem really complicates. So this is like a very high level overview of the optimization opportunities that you would be available in the chip level. When you have a heat sink and a chip, these are the kind of the high level opportunities in optimization that is kind of available. So I would like to start with the optimization because as we go through the data center cooling slides, like this introduction to optimization might help people to identify the opportunities that is available for them in each of the cooling techniques that we are bound to discuss. So what is optimization? As we all know, optimization is an action or a process of determining the best solution for a given problem subject to constraints. And the optimization can maximize or minimize a function, right? Like most of the times the optimization is posed as a mathematical problem. So you would either decide to maximize or minimize a function. So why is optimization even important? So oftentimes like optimization is done just for the sake of having a novelty in the work. So every working system requires optimization is completely a myth. There are certain systems which can be left unoptimized. So the most important step in an optimization process is to find out if the chosen system really requires an optimization or not, and how do you do that? So the deviation from standard designs cost more. So most of the times the optimal design deviates from the standard design. So you have to justify why this optimization is very important. So the best optimization algorithm and the optimal designs are often nature inspired. So the nature is smarter than what we think. So I think the nature has all the best and optimal solutions hidden, and then we just try to get inspired from the nature optimizations, and the best optimization algorithm henceforth is derived from that. And the solution, so when we look at the optimization solutions, and on if you fix the y-axis as a performance, you have this ideal solution from the theory or nature giving you the best performance, and you also have the solution that works. Like for example, if you take this on in a heat transfer context, so you know that even before you attempt to optimize a heat sink from an ideal solution or from theory, you know this could be the best performance, and you have a heat sink for which the solution is known. So there is a solution that works. So your optimal solution would lie somewhere in between your ideal solution and the solution that works. And the gap that you see between the ideal solution and the optimal solution is because of the constraints and the uncertainty. So most of the times the optimization process is associated with quantifying the uncertainties and also like quantifying the constraints under which this optimal solution is really valid. So the nature has the best solution, as I said before. Now, oftentimes in the state of the art literatures, if you see the major flow of this optimization process begins with a physics-based model. So once you have a physics-based model, you can generate a lot of data, and that data is actually employed to develop a surrogate model. So once the surrogate model is developed, a surrogate model is expected to represent the physics, and the physics-based model is expected to represent the data. So there is always a looping between the physics-based model and the surrogate model. And this process is known as regression, right? Like you are trying to develop a mathematical function out of a complicated CFD solution or the governing equation. So your optimal solution is as good as your regression. So this is kind of the most important or the vital steps in the whole process of optimization. And for the surrogate model, I think the most famous surrogate model that you can see in the literature is an artificial neural networks, oftentimes that is being employed for a non-linear optimization problems. And the next step after you build a surrogate model is to go for optimization. And this optimization involves algorithms, right? So these algorithms, there are a lot of algorithms that are being developed and are currently being employed. But I would like to touch upon genetic algorithms because that's what I have been using throughout my research, right from my PhD and even in my postdoctoral research. And once the optimization process is complete, then we go to the optimal design, and then we go ahead to verify the optimal design. So I would just like to emphasize more on the regression because your regression actually determines the accuracy of your optimal design itself. So the common objectives and constraints that you can encounter in real life are going to be like the weight. So you always want to minimize the weight and minimize the size. Also, you want to optimize the rate of energy consumption. You want to optimize the heat transfer rate. You kind of want to optimize the efficiency of the COP, and you want to you minimize the cost incurred and optimize the system performance. And the commonly encountered constraints are going to be like you have a specific space, you have a given material, and the time also becomes a constraint in transient problems. And the manufacturability and the reliability are the two important constraints that is often overlooked in academics and are very important when you come into industrial research. So all of your optimization have to satisfy all the constraints, and the constraints play a major role in determining the optimal solution than the objectives itself. So the constraints are more important than the objectives. So the common terms and definitions in optimizations are going to be like the search space, the objective function, constraints, systems, subsystems, trade-off, the Pareto optimal solutions, and the non-dominated solutions. So what are these? So these are the kind of terms and definitions that you use when you mathematically transform your heat transfer problem using a surrogate model, right? Like the search space kind of tells you the bound space within which you can search your solution or your solution lies. And the search space is actually determined by the constraints. And the objective function is a mathematical representation of the goal of your problem. And the constraints are the mathematical representations of the limiting conditions. and a system and a subsystem, right? So the system is nothing but a set of things or components working together. So a system can consist of multiple subsystems. And what is a subsystem? It's an individual component or the part of the system. And the next important thing is the trade-off, right? So a trade-off is nothing but it's a situation involving betterment of one objective at the cost of another objective, right? Like we always talk about a trade-off. So when you gain something, you lose something. That's the philosophy that's underlying for a trade-off. And Pareto optimal solutions. So what are the Pareto optimal solutions? They are the solutions for which any improvement in one objective degrades at least one or more objective, right? And the non-dominated solutions, a point for which there does not exist any other feasible point better than it. So the trade-off, the Pareto optimal solution, the non-dominated solutions are always pertaining to multi-objective optimization, but the other terms are kind of pertain to both single objective and multi-objective optimization. So now let's get into data center. So the common terms and definitions used in data center are going to be the cold plate, the thermal resistance and the thermal budget, and aisle, die, hotspot, and CRAH. So oftentimes we talk about heat sinks. So the terminology cold plate refers to a liquid cooled microchannel, right? Like they have extended surfaces and they have channels in between them. And then when you have a liquid that cools them, it's called a cold plate. And the thermal resistance. So the thermal resistance is mathematically defined as the ratio of the thermal budget to the heat transfer under steady state, right? So, and the thermal budget is nothing but mathematically defined as the difference between the chip and the ambient fluid temperature. And in data center, we always talk about aisle. So the aisle is nothing but the passage between two server racks in a data center. And a die is, when we talk about die, it's about a heat generating component or a chip. And a hotspot is the hottest part of the chip or the die. And CRAH abbreviates as computer room air handling unit. So these are the basic terminologies that you may be required to know as we go through the slides that is going to come, because like the most of the slides would contain this common terms and definitions of the optimization as well as the data center. So I thought like giving you an introduction beforehand would help you understand the forthcoming slides. So there is always this assumptions versus reality, right? So in optimization, a textbook problem is very different from an actual research problem. So the assumptions that most of us make to simplify a problem is going to be like the objectives are always single objective. But in reality, most of the real world problems are multi-objective. And converting this multi-objective into single objective is still good, an approximation, but then a real world accurate optimal problem requires you to solve the multiple objectives simultaneously. And you also have this assumption of a single variable optimization problem, but in reality it's multivariable. So, and also in reality, when you talk about optimization, we assume that no subsystems interact. But in reality, the subsystems are highly interacting, and I have a very unique slide to show you the interaction of the subsystems. And we often assume that the optimization problem is linear, but in reality, it's highly nonlinear. And we always assume a single constraint, but in reality, most of the problems are multiple constraints. So in electronic cooling, topic is not complete without we touching the Moore's law, because the Moore's law predicts that the number of transistors per square inch on the integrated circuits had doubled every year since their invention. And as I already mentioned, the heat of a chip, the heat generated from a chip, is a function of how much transistors are we packing in the given footprint. So the Moore's law predicts that this trend will continue into the foreseeable future. And often this statement is debated right now, talking about the longevity of the Moore's law. So there are a certain section of the people trying to keep this Moore's law to continue by adopting various techniques. And there are some sect of the people who already believe that the Moore's law has come to an end. But I think this is a very important law that kind of lays a roadmap on the direction of how the electronic cooling thermal management has to progress. So this is a very nice figure that shows the evolution of this Moore's law and of the chips that have been prominent in each of the decades. So we start with 1970s, as you can see. On the y-axis, you have this number of transistors, and on the x-axis you have this year. So in 1970s, you can see like the processors. I think they just had like less than 10 transistors per chip. And now, if you look at the exponential growth, since it's a log scale, you just see a linear line, and we have reached about like 10 power 7 transistors per chip. And this is really alarming because of the fact that you're able to pack more and more transistors into a single chip. The power dissipation has hugely increased because the power per transistor hasn't decreased at the rate at which the number of transistors per chip has increased. So, and this is another way of putting things up. So once you start this, like if you look at the transistor size, we started from 10,000 nanometers, and we have just boiled down to like 4 nanometers. And right now, I think Intel's 14 nanometer chip is kind of like it's a prominently used chip, and we have also gotten down to like 11 nanometers and 7 nanometers. But then once you keep decreasing the transistor size, you also reach the size of one atom, right? Like, so at some point your ability to transfer electrons across the transistor is going to diminish, and that's why there is always a limit up to which size you can shrink the transistors, right? So now, as you see here, this is a 7 nanometer transistor and this is a 5 nanometer transistor, and we have superimposed them onto an approximate size of an HIV virus. So this is the size which the modern computers are dealing with. So the number of transistors continues to increase for now, and the power consumption has actually plateaued because the transistor size has a limit, and therefore the power consumption has also plateaued. And now we are moving towards something called the multi-core solutions, which gives rise to something called the heterogeneous integration. So the main point from this slide is that the number of transistors that can be put onto a single chip has increased. The power consumption per transistor hasn't dropped at a corresponding rate, which means the number of transistors dominate the power consumption per transistor. Therefore, the power from a single chip has continued to increase. So the amount of power per transistor has dropped, but more slowly than the size of the transistor has shrunk. So you can like put billions of transistors on a chip, but you can't use all of those transistors at the same time. So this gave rise to the concepts of CPUs and GPUs. They are dedicated core points in your chip, where you can have a portion of your chip dedicated to a CPU or a GPU, and then they are going to be the highest power generating portions of your whole chip, right? So this gave rise to a concept of heterogeneous multi-core. So the typical solution to this issue is to have dedicated asynchronous co-processors, right? The GPU is one such example. So combining functionalities and combining different functionalities onto a single chip is actually the trend that is going to set this Moore's law to continue. So Moore's law, is it still valid? So as we now understand from the slides, that the functionality is a function of the number of transistors that you're able to pack in a given chip area. And the top of the line microprocessor currently have the circuit features that are around like 14 nanometers. But by the early 2020s, there have been speculations that we might get into this 2 to 3 nanometer limit, right? So this gives birth to heterogeneous integration. So when we talk about heterogeneous multiprocess, we need to define what a heterogeneous integration is. So heterogeneous integration is like is the process of combining multiple different functionalities onto a single chip, either vertically or horizontally. So you have multiple functionalities, and you can have a single chip with multiple core areas, and all of that single chip could perform the function of multiple things like your CPU, GPU, memory, and all of the things. So now this is the fundamental thing to understand when we talk about the data center thermal management. So what is a data center? So data center is a facility that houses large servers and high performance computing processors. So when we say high performance computing processors, they are a victim of this Moore's law, right? So that's why understanding the Moore's law and understanding the data center go well with each other. And why do we need a data center? So a modern day life in this digital era is impossible without data centers, right? So when do we use a data center? When the information search on an internet. So whenever you search an information on the internet, or during an e-ticket reservation, during a stock trading, and during an online money transaction and online shopping or whatnot. So even while we are speaking on this video call, there is a functional data center that stores data. So data center has become an inevitable part of our modern day life, and that's why the data center thermal management is very important. So the data center requires uninterrupted zero downtime operation, and interruption caused by the equipment failure would entail costly repairs, right? So you can't blame anyone because any interruption that is caused either by thermal or power failure is going to cost more. And even so is the business that gets interrupted. So for uninterrupted operation, two things are crucial. So one is the power supply and other is the cooling. So the trade-off between power and cooling is well explained by the laws of thermodynamics, right? So there is a trade-off that exists, and uninterrupted power is assured by having several backup sources of power that can automatically brought on as soon as when you have a power failure. But then cooling is a more complex issue. So that's why the thermal management of data center attracts a lot of funding, and there are a lot of innovative areas which you can explore whenever you have this thermal management of data centers, as it is a very much complex issue than the power. So, and the motivation to take up the data center thermal management is like, for most of the electronics to function properly, it needs to be cooled and kept at an acceptable temperature level, as we all know. I think there are there is a problem of overheating, and the overheating at a specific location because of the heterogeneous integration, because you have specific parts of the chip that is going to be like dissipating high amount of power. And overcooling and undercooling are both serious problems. I think undercooling is considered more a serious issue, but overcooling should also receive attention. Like for instance, if you see this below figure, this blue bar, the blue rectangle can be considered as a chip, and this red spot on the blue chip is the hottest part of the chip. And and most often times the thermal engineers decide where to bring the cold fluid. So the most efficient ways to cool is to bring the coldest fluid to the hottest point, and that way you also bring down the caloric resistance, and that's the most efficient way to do. But the thing is, all the regions need not receive the coldest fluid, right? That's what we call as overcooling. So if you can bring the coldest fluid to all portions of the chip, and there are certain portions of the chip that are overcooled, and there will be a certain portion that is undercooled. So that's the issue that we are talking about in this slide. And the assumptions versus reality for electronic cooling is like, oftentimes we assume there is a uniform chip heat flux, but in reality, because of the heterogeneous integration to keep up the Moore's law going, we have a lot of hot spots on the chip. Unless they are spread well, they can't be considered as a uniform heat flux. And the other assumption that we make is also steady state. And in most often times, there are intermittent peak loads, which means there are transient power that go on and off at a particular time interval. And also we make some assumptions on the heat loss. We say there is no or constant heat loss. But in reality, most of the problems have this time varying heat loss. So I think the attentions have to be given to all of these details in reality. And that's where the research in data center cooling has gotten very interesting in this day and age. So this is a general data center layout that I had to borrow from one of the books. So as you can see here, there is an incoming grid power that supplies the power to all the systems that you can find on the data center. But our special attention is actually given to the small room that houses like a lot of servers in the form of racks and aisles, right? So this black region having these racks is our area of attention, because that's where we really want to apply all our thermal management techniques. And this kind of figure you can find a lot in most of the books and even on the internet. So I just had to borrow one to just show you. And our Binghamton University in New York has this particular data center layout. So we have like 4 aisles. So as I already told you, aisles are nothing but the passages between 2 servers. So we have 4 aisles, and each of these aisles are being dedicated to one function. Like for example, this aisle D is dedicated to storage. Aisle C is for computation, Aisle A and Aisle B are for network. So each of these have different servers and different variety of chips that are dissipating power, and all of the characteristics of the chips are really different, right? Like the computing aisle could be the most critical part of this data center because of its high heat dissipating capability, and this cannot be undercooled. So as I was talking about this undercooling and overcooling problem, so we need to make sure that this is properly cooled, and this remains the most critical part of the data center. And this is the flow of power and chilled water inside a data center. And this, as I told you, this is a rectangle housing the data center. The server racks are our area of interest. So you want to make sure that you thermally management the racks and the servers in this small area. So let's talk about the different scales available in data center thermal management. So we start from scale 1, right? So the scale 1 is the chip. And if you look at scale 5, it's the room that I was terming it as the specific area of interest. So from scale 1 to scale 5, like everything is so monotonous that any changes or any optimization that we do in scale 1 is reflected in scale 5. So let's go each scale. So the scale 1 talks about the chip. The scale 2 talks about a blade or a server. And the scale 3 talks about the grouping of different servers called as the chases, and the scale 4 is grouping of different chases to form a rack, and the scale 5 is nothing but grouping different racks to form a data center, right? So these are the different scales at which you can do a thermal management, and the scale 1 optimization benefits are seen at scale 5. So if the scale 5 airflow is managed well, but if the heat sink is not optimized, you will lose out on the performance. So I think each of the scale, optimizing at any scale is critically very important for all the other scales. So this is something you can take it as a system and a subsystem. So if you consider this whole room, the cabinet that is shown here as a system, there are various subsystems which are operating simultaneously. And it's very important for us to start cooling from the chip level. So this is the in-house server rack that we have in the Binghamton University. As you can see, these are the different racks that are being stacked together. And these are the perforated tiles that you see in the bottom. And this wirings are nothing but the instrumentations that we do to measure the temperature and the flow rate for each of the server. And these are to just simply make some measurements. And this are for the fluid supply. If the fluid has to enter and exit the server, we also have some manifold arrangement. And these, the right-hand side figure shows like what is the power dissipation capabilities of each of the servers that you see here. So some servers are high power dissipating, some servers are low power dissipating, but then they're all stacked together. So this is kind of a heterogeneous integration in the rack level, right? So when we are talking about the heterogeneous integration chip level, you also have heterogeneous integration in the rack level, like different functionalities of different power dissipating capabilities stacked together and forming a single rack. So now let's see how the Moore's law gets reflected on the server level. So if you take the y-axis to be the heat load in kilowatt per rack, and as the x-axis as a year, as you can see for 1U server, the 1U indicates the height of the server, right? So when you look at that, as you can see, there is an exponential increase in the heat load in kilowatt per rack, and then it started to plateau. So in 2014, it was somewhere around 37 kilowatt. I think in 2020, it has gone as high as like 60 kilowatts. So which means it has kind of exponentially increased and then starting to plateau. So this is the effect of the Moore's law that is reflected on the server level. So I think this could be a motivation to why we need to cool something at the chip level. So now, how cooling is traditionally done in a data center. So the normally cooling air enters a server rack through the front face and the hot air exits from the rear face, right? So to do all this efficiently, there is a clever concept called the race flow data center. So what is a race flow data center is that you have a plenum, and then you try to pass the cold air through a raised flow data center from the bottom. So this gives you the leverage to kind of direct the airflow to the desired regions efficiently in a data center. And the air conditioners are used to pump the cold air into the space below the raised flow. And the raised flow data center are also proven to give more flexibility. So the main question when you use a raised flow data center is how efficiently you can channelize the cold air to the hotspot. So these are called the hotspot targeted cooling, where you don't want to undercool a really heat dissipating server, right? So how efficiently you can channelize is I think it's a day and age research. And this could give you a quick visual of how the airflow, the raised flow data center thermal management kind of works. So if you see, this is an air conditioning unit, and there is an airflow that is being pumped through the plenum, and that is being taken up by the servers by the raised floor. And you have this perforated tiles, which kind of gives you a passage for the cold air to contact the hot servers. And then these hot airs are collected on the front face, and since the hot air rises, and these are taken back into the air conditioning unit, and then they are cooled, and then they are blown again. So this is a process that happens, and you have a lot of challenges in this, right? Like as you can see, there is a bypass of this cold air, and there is also this recirculation of the hot air, right? So this bypass and recirculation kind of causes this hot air and the cold air to mix with each other, which kind of brings down the efficiency of the data center cooling. So the tile design, I think it's one of the research areas where you have a lot of opportunities to optimize. And there is this underflow design, which is another interesting area to optimize, and the air temperature, right? So to how well you can manage the air temperature. And when we are talking about the desired qualities of the data center, I think flexibility is one of the desired qualities. So I think it's an important characteristic of an efficient data center. So this raised floor arrangement actually gives unlimited flexibility, right? So what is flexibility? So whenever there are certain servers or racks being replaced constantly, your data center thermal management should still hold good, because most of the times the servers become outdated in a couple of years, and there are certain servers that are being replaced. So there needs to be, when you construct a data center, and it needs to have a permanent ducting for all the airflow and the raised flow design, such that you can close and open the tiles, and whatever servers gets replaced or moved, your data center thermal management should still make sense and currency, right? So that's the flexibility that we are talking about. So typically 10% of the equipment in a data center is replaced each month. So it's very critical. So you can't say like this data center was designed to cool a servers of 10 kilowatt each. You may never know, like in a year you could have a server that is like 50 kilowatt each, and your thermal management should still be able to adapt and continue. So to efficiently channelize the flow and to overcome the problem of the hot air mixing with the cold air, there have been techniques on the containment, right? So they term it as this containment techniques. So the containment techniques are done in two ways. One is the cold aisle containment. So whenever there is a cold air that is blown from the underfoot plenum and through the perforated tiles, whenever they reach the servers, they are contained such that there is no bypass of this cold air to the back of the server to mix with the hot air, right? So this is one technique, and the other technique is to contain the hot air, right? So if you can contain the cold aisle, you can also contain the hot aisle, and this hot aisle makes sure that the hot air is contained and there is no recirculation of that into the cold aisle, so that they don't mix with each other. So these are the two strategies that are being done to kind of efficiently make sure that there is no mixing of the cold air and the hot air. But then which technique is the best is determined by the energy consumption, and it has been reported that the hot aisle containment consumes less energy compared to the cold aisle containment. So this blue bar graph represents the hot aisle containment, and this maroon represents the cold aisle containment. So for the chiller, the hot aisle containment consumes less energy. So a data center designed for hot aisle containment is actually more efficient, and it's been reported in the literatures also. So this is a schematic of the cold aisle containment. I just want to show this visually how this happens. So as you can see, the cold air is being contained, and it's prevented from mixing from the hot air, right? So this prevents mixing basically. Now, as you saw on the first initial slides, that controlling the initial temperature or the incoming temperature of the fluid, it also requires power. And the lesser the temperature of the fluid is more desirable, as you can reach more cooling power. But then there are some standard ambient conditions, and the standardization always leads to optimal conditions. So they kind of give us the guidelines on what could be the optimal operating condition inside the data center. So too much moisture in the air can lead to condensation, which will eventually corrode and short out the electrical systems. And dry air is also not desired, right? So adjusting the climate controls to reduce moisture may seem like a solution, but that can lead to problems as well. So if the air becomes too dry, then you have the static electricity that build up, and which can also cause equipment damage. So with regard to humidity and also with regard to temperature, which are psychrometrically kind of dependent, so you have this like optimal operating condition in which you want to operate your data center. So according to the American Society of Heating, Refrigeration and Air Conditioning Engineers, the recommended and the acceptable operating temperature ranges from somewhere between 18 degrees to 27 degrees. So that can be the inlet temperature of your air to safely operate your data center, to avoid condensation as well as the static charge deposition. So, and also with regard to humidity, I think the maximum humidity is 50%, that's recommended, and like 80% that is recommended, I'm sorry, and the minimum can be 20%. So on average, 50% humidity within data center are kind of recommended. But there is a concept called this free cooling, where people can just take the ambient air inside the data center after so much of filtering, and that creates humidity in the air of the data center, right? So because the ambient air could not and need not be in the humidity range that is being suggested. So when we're using a free cooling, so if you want to look at the basic definition of a free cooling is nothing but making use of the freely available ambient air for cooling the data center. So this is exclusively being done only in certain geographies, right? You can't do it in all regions of the world. Only in some regions of the world, when the ambient conditions are right and allows the data center to cool without any refrigeration plant. And this ambient air is thoroughly filtered and humidified by the evaporative coolers before they even enter the data center. So there is a lot of a process that happens between the air being sucked in and the air being delivered to the data center. So I think the free cooling, like it also depends on the geography, as I told you. So most of the northeastern America continent can make use of the free cooling, and some parts of the Europe can also make use of this free cooling. So building a data center at the region where you can make use of the ambient air could be more efficient for you in terms of energy consumption as well as cost. So like as we discussed the hotspots in chip level, there is also hotspots in data centers, right? As I told you, like the data center servers are getting replaced. So there could be a low power server that is being removed and replaced with a high power server. And that could immediately become a hotspot in your data center. So channelizing your airflow and detecting the hotspots in the data center is very essential for better thermal management. When we talk about this airflow management, there are certain questions and some opportunities, right? So the race flow design makes it possible to create, but does not guarantee proper cooling of the server racks. So the questions that we might have is like, how much cold air do we need in terms of CFM? And how does it distribute well in the whole data center? And are we meeting the individual demands of all the server racks that are being updated? And does the cold air introduced at the floor level reach to the top of the 2-meter tall server rack? Like, because you're bringing the air from the bottom, so you have to make sure it reaches the top portion of the servers also. And can the hot air coming out of the one rack enter the inlet of the another rack and damage its cooling? And one detects hot spots and tries to force cold air there by placing more perforated tiles. So if that fails, an extra air conditioner is installed in the hope of removing the hotspot, right? So the hotspots always get like kind of a special attention. So you're trying to direct more cold air, and if not, if it's required, you also place a special air conditioner And it is estimated that the amount of cooling air used in most data centers is 2.5 times the required amount, which is a problem of overcooling that we were discussing few slides before. So there's a good opportunity for saving air conditioning equipment and energy, which requires a very detailed optimization in the data center level. Whereas until now, uninterrupted operation of the data center was the only focus. But I think the recent literatures have started to address the problem of overcooling, where we are moving towards something called the green data center, right? That's also a new goal that I think most of the research academic papers that are getting published are being focusing on. So now, since that's the high level overview of this airflow thermal management with regard to data center system. Now when we get into a server, this is what you see. Like, this is a server that is opened from my university at Binghamton. Like they have, like, if you see, there are two heat generating units on which two cold plates are installed. So they have micro channels, and we have been using liquid water to cool these servers. And this is what you see inside a server. So these are the fans that are blowing air, and these are a special CPU cores that are being cooled by liquid. So what does it mean? So when you have a liquid cooling in a server, that is always assisted by an airflow. So they are called airflow assisted liquid cooled data centers. So you have this liquid cooling happening within a server, right? This is the area of the hotspot which requires a special attention. Now, the heat sink scale. So if you want to choose between two technologies that are widely used now, which is the air cooling and the liquid cooling, I think this is the scale at which you physically get to look at the two heat sinks. So an air cooled heat sink is, you can see, is like at least 20 to 30 times bigger than the liquid cooled heat sink in terms of volume, right? Like, so this is a liquid cooled heat sink. When it's kept aside air cooled heat sink, you can see the size difference. And that's why the liquid cooled heat sinks are really attractive in terms of optimization, because now if you remember the initial slide, we were talking about the area. This could provide the maximum H in a very small area, because we're using microchannels and we are forcing liquid water, which has superior thermal properties compared to air. So, but it also has its own trade-off, that it's going to require a high pumping power, as well as it could be prone to leaks. That's why in some systems, if you know the power estimation, air cooling is still preferable. But this is kind of a physical comparison that I would like to show between an air cooled and a liquid cooled heat sink. And so when we want to compare different technologies, on the x-axis you have this watts per centimeter square of the heat that each of the technology can remove, and on the y-axis you have this not so easily quantifiable quantities like complexity, cost, and risk, right? So as you can see, when you move from a forced air cooling to something like a liquid cooling, you're actually trying to move vertically up on this axis, also horizontally. So as you're able to remove more and more power, the complexity associated with the cooling is also increasing. And this kind of lays a map or a roadmap to understand what are all the limits of different cooling technologies that we can employ. And the liquid cooling and the two-phase cooling directly on the chip seems to be the removing high heat flux, but it also has its own complexity and risk. And the air cooling is less risky, so it's most of the times it's preferred. Now, so when we get into a server, and this is kind of an exploded view of the components that you get to see, right? So the optimization opportunities for heterogeneously integrated packages, I've tried to list it here. So on the right hand side of this figure, you can see the kind of the objective functions that is usually encountered, and on the left hand side you would see the constraints. So you can move from bottom to the top on this figure. So if you talk about the active devices, cores, or the multi-chip modules, the things that you get to optimize are the microchannel design, right? Like, for example, the technology one here is like trying to bring the cooling solution directly onto this device. So these are called the embedded cooling solutions, where you don't require anything above this, like all the STIM1, IHs, and the heat sink, everything can be removed, and the heat sink is integrated onto this active device. So there, the optimization opportunities that you have are the microchannel design, and the choice of the dielectric fluid, right? So because once you're bringing your cooling technology onto this active device, you can no more use water because of its bad dielectric properties, and you have to make use of dielectric fluorocarbons, and they might have inferior thermal properties compared to water, but that's what you can use when you want to embed the cooling solution. And they are constrained by the chip size, right? Like the choice of fluid and the chip size, which is the surface area. Now, and then as you move up the figure, the second technology that you might encounter is embedding the cooling solution onto the lid. So you have this active device, there is a thermal interface material, and then there is a lid, which is called as the integrated heat spreader. So you can try to embed your cooling solutions on the top of this lid, and you have the same objective functions and the same constraints. So they're all constrained by the area, and the objective function is to optimize the microchannel design. And then you move further up, and then once you reach this point where you want to have a spreader, I think that's the technology 3. And there are a lot of interesting research that is happening with regard to reducing the spreading resistance. And the main objective here is to increase the effective thermal conductivity. You want to achieve high thermal conductivity. And I think the state-of-the-art technique are using the vapor chambers, right? They are the state-of-the-art techniques to kind of spread the heat efficiently from a single hotspot to a very large area by having a high thermal conductivity because of the two-phase mechanism. And they are again constrained by the available area and the thickness, right? Because this area is again a constraint. And when you move again vertically up, you have this the last technology, which is the most commonly used technology, is by attaching a remote cooled cold plate or a heat sink on the top of the spreader. So you go through all this conduction, sequential conduction resistance, and then you reach this technology 4. And again, the things that you want to optimize, your objective is going to be the optimal microchannel design, and you want to minimize the total resistance, and your constraints are going to be the available area, height, and the pressure drop. So all of these objectives that you see here are constrained by available area and the footprint, right? Like even if you choose a technology 1, you have constrained by the area, and even the technology 4, you have this overall footprint that is constraining you. So I think these are all the 4 major technologies that are being employed now. And it's also less complex when you move from the bottom to top again, right? So when you have this, when you move from technology 1 to 4, you're also reducing the complexity and the risk, but also you're reducing the heat that you can remove. So that's the kind of trade-off that this figure is trying to address. And when we talk about steady state, it's also important to talk about the optimization opportunities available in the transient thermal management. Right. So when we talk about the transient thermal management, is by using a solid liquid phase change material based composite to kind of remove the intermittent peak load. So from theory, you know that the ideal melting time will depend on the mass of the PCM that you use and the latent heat of the PCM that you choose and the heat input that it's going to receive. So I think for a transient thermal management, the level 1 optimization would try to determine the optimal PCM to the metal volume ratio. Like there are a lot of literatures that are discussing what's going to be the optimal PCM to the metal volume ratio to optimize the heat sink. And the level 2 optimization will talk about like it would fix the volume ratio, because from this optimization you would determine what is the optimal PCM to the metal volume ratio, and you would fix the volume ratio and determine the optimal geometry or the morphology of the TC. Like either you want to use a plate fin or a pin fin or a porous media, for example. So the morphology that you want to use for a fixed volume ratio of the metal is something that you can do on the level 2 optimization. And this is constrained by the maximum volume of the PCM that is available in this composite. And the thermal conductivity enhancers can be in the form of metallic fins and porous media, right? So, and in general, like for the operation point of view, these are the 2 objectives that you will encounter. So the objective 1 is to maximize the phase change time during the melting without exceeding the device safe operating temperature. And the objective 2 might be to minimize the solidification time, the time it takes to cool back. So this often requires an active assistance, which means you require an external heat transfer coefficient to bring down the solidification time. Though you can optimize the geometry of the morphology to reduce the solidification time, but it's not so efficient. You might often require an active assistance for this objective. So a design that is optimal during the melting phase need not be the optimal during the pre and the post melting phase. So that this is a really challenging optimization problem, because when you talk about the phase change material based composite, you want to discuss about the morphology or the optimal morphology that can meet the objective 1 and objective 2. It has to perform well during the melting as well as the solidification is a real challenge. So now, when we know about all the technologies that are available before us for the given thermal management problem, I think the cooling problem can often be disregarded into 3 technologies. Often it could either be the air, liquid, or the air-assisted liquid cooling. But what determines the technology, the right use of technology, or the constraints? And the constraints are going to be in terms of reliability, cost, and manufacturability, right? So any technology that you propose have to pass this constraint and become the optimal technology. So if there could be a technology that could be very good from a heat transfer point of view, but if it's not manufacturable, then it could not pass the test and then become the optimal technology. So the constraints drive the choice of optimal technology more than the objective itself. And when you try to take an academia research into an industry point of view, I think the reliability, cost, and manufacturability play an important role in determining the choice of your technology. And these are the heat sink. When you use a heat sink or a cold plate, often the resistances are being categorized into conduction, convection, and the caloric resistance. And these definitions are well known from the textbooks. And these are the high-level overview of what we are trying to minimize. So we want to minimize the summation of all these resistances that we encounter in the heat sink or the cold plate. So when we are talking about the trade-offs and the systems and the subsystems, like if you're trying to increase the area of your heat sink, let's assume that this is the spreading resistance. So when you increase the area of the heat sink, the spreader, as you see on one of the schematics, the spreading resistance increases. But fortunately, once you're increasing the area, the heat sink resistance decreases, right? So you see the heat sink resistance drops with increasing area ratio, and the spreading resistance increasing with increasing area ratio. And then if you're posing a constraint on the area, because most of the time the area is constrained, so this is going to be the region at which you want to find your optimal. So do we understand the conflict? Because when you're dealing with 2 subsystems, one is the spreader and other is the heat sink, for a given variable, which is the area ratio, by increasing the area ratio, one of the resistance might increase and other might decrease, but your objective is to minimize the summation of both. So when you're trying to combine 2 objectives into a single plot, this is the feasible region in which you want to resolve the trade-off. And understanding the conflict is very important when you're doing an optimization problem. So this is the region of conflict that I was trying to highlight in the previous figure. So on the left, you see the spreading resistance, and on the right, you see the heat sink resistance, and you want to kind of minimize the summation. So either you can try to minimize both of them simultaneously, or pick a solution that is going to be kind of favorable for both of the 2 resistances. So identifying and resolving the conflict becomes a prime focus of multi-objective optimization problems. And the 2 objectives are sometimes combined, right? So, or solved simultaneously. And I would recommend solving simultaneously could lead to more accurate optimal results than combining the 2 objectives. When we are talking about the trade-offs, so I just tried to pick 3 subsystems from the package. One is the heat sink, the spreader, and the thermal interface material. You can see that they are all having their own trade-offs. So a heat sink requires high surface area, and the spreader requires a low surface area, right, for it to be optimal. And these 2 are going to operate simultaneously with each other. So when you're trying to come up with a design saying that the area is going to be small, then you're actually giving up on the heat sink resistance and then doing good for the spreader. So but when they are going to operate simultaneously, that's why understanding this trade-off is very important. So you have to propose a surface area that is going to be optimal for both of them, which are highly conflicting. And if you look between the spreader and the TIM, so the spreader we want it to be kind of be in optimal thickness, but the TIM has to be like a very low thickness, right? So this has to be very low thickness and high conduction. So they are going to operate with each other. So we need to look at the optimization parameters or the objective functions of this subsystem, which is the TIM. Like when I do this, what happens to the spreader? And now when I try to optimize the spreader, what happens to the heat sink is something that we need to keep an eye out. And if you can identify a parameter like the surface area, which is going to be conflicting for both of the subsystem, then you have an optimization problem in front of you, which would be very interesting to optimize. So now, if we are moving towards the advanced technology with respect to data center cooling, as I was trying to highlight in one of the figures, the embedded cooling is receiving a lot of attention because it's often termed as a chip implant cooling. So what happens in an embedded cooling is that the heat sink is directly mounted on the heat source. So the intermediate conduction resistance is all removed, and the heat sink directly is mounted on the heat source. So how it is done? This can be done by a lot of advanced manufacturing technologies, such that the additive manufacturing or the laser printing, and they can be etched and they can be an integral part of the chip. So the advantage, as I told you, is that it's going to eliminate all the sequential resistance in between the heat source and the heat sink. And however, it poses a technological risk, right? Because there are some active circuits, and when you try to bring the fluid in close contact with the active circuits, then you are in a real trouble. So that's why you want to use a dielectric fluid. And when you use a dielectric fluid, you're losing out on the heat transfer performance compared to water. And it's always associated with the technological risk of the cooling coming in contact with the chip. And the other advanced technology with regard to heterogeneous integration is going to be the three-dimensional integrated circuits. So the three-dimensional integrated circuits is nothing but heterogeneous integration in the vertical manner. Like you're trying to stack up chips one over each other. So if you look at this figure on the left, so if you have a printed circuit board, you could arrange the chips and like aside to each other on the plane. So they are in plane, are arranged with a certain gap. But a three-dimensional integration is like you're trying to stack the chips one over each other. So there is a high technological risk with respect to thermal as well as the electrical things, right? Because each of the chips could be of different functionality. So you're trying to stack a CPU over a memory. You're trying to stack a GPU over a CPU, which are all having different functionalities, and all of these could come from different manufacturers. So for them to communicate with each other and for them to be thermally managed, I think it poses a very high technological risk, and there is a lot of scope to optimize with regard to three-dimensional integrated circuits. So I think these are gaining attention, at least in the portable electronics. I think smartphones are a great example of 3D stacked chips. I think Samsung has one of its smartphone having this three-dimensional integrated chip technology installed. So when you have this data and optimization, I think we went through this slide in the starting, but just to give a recap, there is a physics-based model and you want to develop a surrogate model, and the surrogate model has to represent the physics, and then we do the optimization and arrive at the optimal design. So the data and the data reduction play a very important role in the optimization. So when you have a data, there is a way that you take this data, do a surrogate model, and then do the optimization. This is one way of doing that, right? So you can directly feed this data into a neural network or any of your polynomial regression algorithms and then do the optimization. The other smart way to do is to take the data and do a data reduction and then do the optimization, because this is a more efficient way. Like for instance, if you have temperature as your data, you can always derive a Nusselt number or a heat transfer coefficient and then try to optimize that, rather than just trying to work with a very fundamental quantity that you directly measure. So because there are two advantages in doing this data reduction, is that you can also get the physical implication of your optimal result. So that is very important when you do an optimization. So I would just like to give a case study on an optimization on the three-dimensional integrated circuits that I recently did and published. So the thermal manager of multi-die stacked disk, like you're trying to stack the dies one over each other, and then you want to do a thermal management. So you're trying to do a thermal management on the chip as well as thermal management in between the chips. So there is an intra-chip and an inter-chip cooling, right? So this is the problem definition, and we have like stacked up layers, and then there are some core layers that are being highlighted on the red. So now, whenever you have those heaters that are being on the each layers, like you can say there are two layers, and in each of the layers you have two hotspots. And I'm trying to find the optimal location of these hotspots so that this could be an input to the electrical engineers who are trying to do the wiring, right? I can, like, from thermal point of view, we can always suggest what is going to be the optimal location of these hotspots in this vertically stacked layers. And what we try to do is like to directly feed in the locations of these heaters and then try to run an analytical model, but we try to do the data reduction with this location. So we try to do a centroid arrangement, and then for each of the arrangement of these hotspots on both the layers, we try to come up with a unique parameter. So a unique geometrical parameters that is going to consider the centroid of the arrangement and the centroid of the each heater, and we try to come up with a physical limiting parameter called the lambda. So when we try to derive lambda for each of the location of these hotspots, then what you're trying to do is a data reduction. So the limiting values of lambda have their own physical implications that you can derive, and you can see what is going to be the optimal value of lambda. Surprisingly, the optimal value of the lambda is not the exact value of the bounds. So most of the times when you do an optimization, like if your optimal value becomes the bound value, then it's a very monotonic and uninteresting optimization problem. But here we try to do different arrangements of the hotspots and then try to derive different values of the lambda, and then we did a neural network based optimization. And like there are two types of optimization that you can do on a heat sink. So one is called the shape optimization. So the shape optimization is optimizing the fin geometry, and the thermal optimization is optimizing the heat source location. So now oftentimes we assume that there is a uniform heat flux, but the real world problems need not be having uniform heat flux. So it's often good to optimize the fin geometry for a uniform heat flux and then do the thermal optimization. So for the optimized fin configuration, you can try to find out the optimal location of the hotspots by trying to move them around the domain. And finally, when you try to find the optimal location of the hotspots, you can always go back and do the shape optimization again for the optimal location of the hotspots, where you can remove or add fins based on the hotspot location. So this is a never-ending loop because we can keep doing this, and this becomes very specific to the kind of chip that we deal with. So the shape optimization and the thermal optimization, doing it simultaneously is called the co-optimization. And this can be an interesting research area that can tell us that when you do a co-optimization, the optimal solution can really be different when you do a single optimization. And this is the roadmap that we often use when we do an optimization. So you start with an existing cold plate, and the first step is to do an experimental characterization. And the second step is to build a CFD model. And using this CFD model, we do the optimization. And once we do the optimization, we validate the optimal design using the numerical validation of this optimal design using the CFD model. And then we also go ahead and build the experiments and verify the optimal using the experimental design. And then we come up with an optimized cold plate. So the optimal now, if you want to dig into the optimization algorithms, I think there are you can categorize them into single objective and multi-objective, right? Like any optimization problem can be categorized into single objective and multi-objective. And for each of this type of optimized problem, you have these techniques. Like there can be a calculus-based technique, there can be a genetic algorithm, and there is also this exhaustive search. So this exhaustive search is not a very smart way of doing an optimization, but it's a very time consuming, but it gives you the most true optimal solution. So it requires a very high computing resource for you to exhaustively search the optimal result. And for the multi-objective, you can see like you can do this NSGA2 and the exhaustive search and the weighted sum. So NSGA2 is a variant of this genetic algorithm, and more often the engineering problems are multi-objective with multiple Pareto optimal solution. So if multiple objectives are not conflicting, it is a single objective optimization problem, right? So this is like the flow chart of a basic genetic algorithm. So you have this population, right? Like this genetic algorithm works in the principle of the survival of the fittest. So for each of the generation, once you have a solution, like the solutions are treated as a population, and then there is a chromosome which has the information of the population, right? So each individual's information is hidden within the chromosome. So this population is taken for evaluation, and you know the fitness value. And then once you know this, there is the GA operators. They are called the mutation, the crossover. So you're trying to generate the offsprings of the population using the GA operators, and then this goes through a lot of generations. So this is a loop it goes through until you find the best optimal solution, right? So this, again, it works on the survival of the fittest. So the parents have to compete with the offsprings, and oftentimes that in the next generation, the parents might be lost because they might become weaker than the offspring. So that is going to be the most efficient genetic algorithm, because you're trying to preserve the most elite candidate throughout this. So this is just a simple introductory slide into the genetic algorithm. I don't want to dive deep into this. I just wanted to give an introduction of the genetic algorithm. And this is another case study where you do multi-chip modules. So most often, if you can see, there is a microchannel and a heatsink on the top. And the optimization of the heatsink geometry are oftentimes done by assuming a constant heat flux at the bottom. But now if you see, this is a recent research that we did here, where we assumed multiple dies. So these are the two regions that are going to generate the heat, and they are very specific in location, right? So when you try to do an optimization for multi-die heat sinks with a specified core location, your optimal geometry could be completely different from an optimal geometry that pertains to a constant heat flux. And that's what we kind of demonstrated from this study. So like a water-cooled multi-die heat sink, I think that's also a kind of new age research that you can do. Like you can try to assume multiple dies rather than a uniform heat flux. So a water-cooled multi-die heatsink with a parallel rectangular microchannel was designed to satisfy the operational requirements, and a shape optimization strategy using the response surface method was used. And the optimization was performed for constant values of the coolant flow rate and all the operating conditions. And you can refer this paper for a more detailed analysis of this optimization study. And as I was stressing about the importance of the regression function on the optimal solutions, I think this figure kind of emphasizes why the regression function could underestimate or overestimate an optimal solution. So this blue region, as you can see here, is being generated by a polynomial regression equation. And this gray region, as you can see here, are being generated by the neural network. And the orange points, orange dots, are the Pareto optimal solutions that we got using the blue region. And if you look at the optimal solutions from the blue region and the optimal solution from the gray region, they are very different. That's because the regression or the functional representation of the blue region, the gray region are way different from each other. That's why the regression function highly determines what the optimal solution is. And the true optimal solution could be way different, right? Like for example, if you see this blue region, which is an output of the polynomial regression equation, had this non-convex region, and we were not able to identify any optimal solution here. But then using a neural network, you got some optimal solutions in this region, indicating that the regression function's inaccuracy could result in a very bad judgment of the optimal solution. So search space is reducing by imposing the constraint, and the importance of the regression function accuracy is clearly depicted in this figure. And the neural networks are highly accurate in representing the problem under consideration, because it was a highly nonlinear problem, and the neural network was very good, because in certain regions you could see an overlap between the blue and the gray region, but in certain regions they are not overlapping. And unfortunately, the regions at which they overlap are the regions that are not satisfying the constraint, because you have this constraint line here. So this is going to be our region of interest, and you see a highly non-overlap thing. So we felt that the neural network is able to be a good regression function than the polynomial equation by itself. And to conclude, I think the future of energy or the cooling technology is going to be bio-inspired. And you can see here, this is like a lung inspired 3D printed part for cooling CO2. And also for the heat sinks that we do for electronic cooling, bio inspired designs using a topology optimization could be of great interest. And that's going to be the next gen research on heat sinks or any type of cooling. So the conclusions from my talk are going to be that there are numerous opportunities to optimize the systems and the subsystems in a traditional data center. And the advanced technologies due to heterogeneous integration poses a high technological risk. And the optimization done with the right data reduction will be highly insightful rather than using the data itself for optimization. So these are the references with which I kind of build my slides. And thank you for your attention. And I would appreciate any questions or feedback from your side. Be happy to answer.
Participants, you can ask questions. If you are unable to ask, you can type in chat box also.
Hello.
Yes.
Hello.
Mohammed Rashid.
Hello.
Hello. Hi,
Am I
Mohammed.
able? Yes, sir. Myself, Dr. Asif from AMU Aligarh. Yes, sir. I am doing work on team. Just I want to know what is the optimization technique to get a better team.
Yeah, I think
I mean,
thanks
in
for
which
bringing.
direction we should proceed for the better team. I'm just have worked on the silicon paste and I'm working on the PCM
Yeah.
as a team.
Okay. So I think the research with respect to TIM is very critical, and it's actually gaining a lot of attention. So as you said that you're working on like based
Yes,
TIM,
sir.
I think the one thing that you need to make sure is that at the temperature at which your chip is operating, it is always desirable for the PCM to kind of become molten, but it should not melt, right? Like there should be a need for the TIM, but it should not melt. And I think adding some additives to the TIM to enhance the thermal conductivity without losing much on the reliability of the TIM, I think it's very important. And also, I think the recent research are employing a surface modified TIM. So you can search these keywords like surface modified heat sinks with TIM for enhancing the thermal conductivity of the TIM. So I think this phase change material based TIM is also an interesting research, but we need to make sure that it doesn't melt at the operating temperature. Rather, it just reflows at the temperature. So that's the kind of thing that you can do. And engineered TIMs are also getting high attention. Like you can try to engineer TIMs by adding some nanoparticles or even some copper powders, a kind of thing to enhance the thermal conductivity is also kind of gaining some attention. I think the research with TIM is very critical for the electronic cooling and for the thermal management. I hope that kind of answered your question. Thank you.
Any other questions from participants?
I have done, sir. I have used the copper oxide nacelles with the silicon paste, and I have
Mohammed, your voice is breaking.
I'm so sorry, Mohammed.
just
Your voice is so breaking, and I'm not able to hear you properly. So, if you can just put up your questions on the chat window, I will be able to kind of
You
respond.
can type in chat window. question is there, Srikanth. Dr.
Yeah,
Srikanth.
yes, Dr. Connery, I'm kind of answering that. I think Ganasai Naidu has a very interesting question, and also there is Darshan. So I'll try to answer it one by one. So Ganasai Naidu asks, is there a chance to use the microchannel cooling in mobile electronic equipment? Ganasai, I think with regard to portable electronics, using an active cooling with microchannel, if that's what you mean, I don't think we have an opportunity for that. I think everything has to be passive with respect to portable electronics. You can still use like micro channels and then try to embed some static or some passive techniques like phase change materials. I think the phase change materials that can melt and solidify inside a channel or a kind of containment have a lot of scope in portable electronics, but then using an active technique, I don't see it coming, because you require an external assistance, and also the space available in portable electronics do not encourage us to use any active devices. So active microchannel cooling is definitely not possible in electronic equipment. And I hope I answered your question. And there is Darshan who asked how to get best optimal solution from multiple Pareto friend graphs. So I think the Pareto friend graphs, if you're talking about the 2D Pareto friend graph, they are just projections of the optimal solutions, right? Like if you consider two objectives and you have a projection, but you also have a third objective, so it could have a projection on the other axis. And to choose the best solution from the Pareto front, you require this high level information called the weights. Like you really want to know what is going to be the weightage for each of the optimal. And there are a lot of clustering algorithms that are available, like for example the Topsis algorithm or the k-means clustering algorithm that can help you cluster the solutions depending on the weightage that you want to give for each of the adjectives. So answering your question, I think you need to look at the clustering algorithms that are available in the literature. Thank you, Darshan. And Muhammad Asif again, so he asked, like, explain what are you talking about adding nanoparticles in thermal paste? Yes. So like adding nanoparticles in thermal paste are, it's like you're trying to build a composite of the thermal interface material. Like the thermal interface materials are inherently with a very low thermal conductivity, right? So you want to have highly conducting nanoparticles that you can try to prepare a composite. And when you try to use that, I think there is, as a composite, there is an effective enhancement in the thermal. And that's what I mean by adding nanoparticles in thermal paste. Maybe I can send you certain literatures that even myself have worked in the recent past, where we talk about some effective TIMs, and I think that should be very helpful for you. Thank you, Mohammed Asif, for bringing up this issue on the TIM, which itself is a separate research area that's kind of receiving a lot of attention. Thank you. Ganasai Naidu, thank you so much. How to handle PCM when used as TIM? So handling PCM when used as TIM is a kind of a big challenge, because you want to contain them, right? That's why I was talking about when you're using a PCM as a TIM, you really want them to reflow, but you don't want them to change phase, right? Like reflow becoming smooth is different from changing phase and melting. So once they're going to melt and solidify, you really want to contain them. So that's going to be a problem for that. So a PCM engineered TIM, I think you can look at this company. I can put this in the chat window. Laid, you can just type this keyword in the internet, and you will get to see a company that kind of manufactures the PCM TIM. And they kind of give a lot of guidelines on how to do that. And I think it would be really useful for them. I can also put the link in the chat window for you. Okay, so I just got the link. So this is Mohammed Asif. If you're listening to this, please follow this link. And this is a very nice company that does this phase change material based TIM, and you can find a lot of research work of them. I just put the link on that. Thank you so much, Mohammed. Thank you.
Yeah, I hope all the questions are clear. Now I thank you, Dr. Srikanth, for your excellent presentation on optimization opportunities in data center thermal management. Uh, Again, thank you for accepting for our invitation and spending your valuable time with us.
Thank
Dr.
you.
Right.
Thank you
Thank
so much, Dr. Kondareddy, for giving me this opportunity. And I really feel happy that you invited me for this talk, because I really consider this as a very precious opportunity to kind of share knowledge with the enthusiastic research community. And also, and I remember you being a very kind and a very helpful senior during my PhD time. I think I joined at the time when you were leaving, and thank you for being such a nice senior to me in my lab, and I learned a lot of things from you. So thanks again for inviting me to this lecture, and thank you everyone for asking me the questions. And Mohammed Asif, if you can go to my Google Scholar page, and if you can try to kind of point out exactly which paper you want, I would be happy to send you. And I can take your email ID from Dr. Kondareddy
Thank you,
and
sir.
give you the papers. Thank you.
Thank you, sir. Thank you so much. Thank you so much.
Thank you so much,
Thank you,
Dr.
sir.
Kondareddy. Yeah.
Thank you, sir. Thank you, sir.
Right, Srikant. Okay. Thank you.
Okay. Bye bye. See you, everyone. Stay safe. Bye bye.
Bye. We have another 5 minutes time. If you people want break, you can take for 5 minutes. Exactly 10:30, we will start session 5.
Yeah, Dr. Reddy, I am ready.
Yes, sir. So just now, previous session completed. I gave 5 minutes
I was
of.
there. I was listening to the presentation.
Okay, sir. 10:30 sharp. We will start, sir.
Sure, I'm ready.
Good morning. I welcome you all for the session 5. I am happy to introduce the session 5 speaker, Professor Samir Khandekar. Professor Samir Khandekar is affiliated to the Department of Mechanical Engineering, IIT Kanpur, India, since September 2004. He completed MTech program from IIT Kanpur, India, 1998 to 2000 in fluid thermal engineering and subsequently earned doctoral degree from University of Stuttgart, Germany from 2000 to 2004. Earlier, after his undergraduate studies in mechanical engineering from Government Engineering College, Jabalpur, Madhya Pradesh, he worked as a marine power plant engineer on board seagoing merchant ships for 4 years, that is from 1994 to 1998. At present, Professor Khandekar is an occupant of Sir M. Visvesvaraya Chair at IIT Kanpur. He is also a fellow of the Indian National Academy of Engineering, elected in 2019, and a fellow of Institution of Engineers India since 2000. He is a recipient of P.K. Kelkar Research Fellowship from IIT Kanpur in 2008, DAD Fellowship 2011, Professor K.N. Sitaramu Award from the Indian Society of Heat and Mass Transfer in 2010, George Grover Medal from the International Heat Pipe Committee in 2007, and a Young Scientist Award, Department of Atomic Energy, India 2005. Professor Khandekar is Associate Editor of International Journal of Thermal Sciences and Interfacial Phenomena and Heat Transfer. He is also an executive member of the International Heat Pipe Committee and Indian Heat and Mass Transfer Society. He has served as an invited faculty member at 5 international universities at Germany, France, Brazil, Russia, and Thailand. He also served as academic senate member of one central and one state-funded autonomous engineering institutes. He has over 85 research publications in international journals, over 100 publications or presentations in international conferences, including 16 keynote lectures or invited talks, 8 patents, and 4 books to his credit. His current research interests are in experimental microscale phase change thermofluidic systems, evaporation, boiling, condensation, heat pipes, and energy systems. He has served as the Associate Dean, Innovation and Incubation, and coordinator of the SIDBI Innovation and Incubation Center, IIT Kanpur, during 2015 to 2017. He is also the president of Shiksha Sopan, a voluntary organization registered NGO serving the deprivileged sections of the society in and around IIT Kanpur. Now I request Professor Samir Khandekar to present the session.
Am I audible, Dr. Reddy?
Yes, sir.
Thank you, Dr. Reddy. I would have loved if you would have made the introduction a bit shorter also, because that's the boring part of the talk. The exciting part of the talk is coming. So I first of all, let me thank you for inviting me. I was also attending the previous lecture, which was also very interesting, which talked on optimization and data centers and what are the challenges which are there. And so my talk is going to move a little bit away from data centers, but the problems remain the same. And we will be talking about some of the contemporary research which I am doing right now with my graduate students. So let me share my screen. Just a moment. Are you able to see it? Hello?
No, sir.
Oh. what is the problem then? Just a moment. I say full screen, and then I have to do present now. Yeah,
Yes, sir. It is there at the bottom.
present now, and then I say my entire screen,
Yes, sir.
and then I say share. Yeah, it's not allowing me to share.
Sir, which device you are using, sir?
Huh?
I am technical team here, sir.
Sir, which device are you using, sir?
Is a laptop or
Normal laptop, a normal laptop.
normal laptop? Are you using Chrome, sir? Google Chrome.
Yes.
In that one, you have to change layout, sir. Near bottom side, one lines is there,
Yes, yes, yes.
and change layout.
Change layout. Change layout. Yes.
Yes, sir.
And
It
then
is
go to,
sidebar is there, sir.
yes.
Just
Yes.
clicking and near bottom, it will showing like present now, sir. Just click present now option.
Yes. Present now. And then my screen. Yes.
Yes.
But then when I'm putting okay, share. Okay. So
Yes, sir. Now it is coming up.
okay. So now I can. Okay. Is it visible now?
Yes, sir. It is visible, sir.
Okay. Good. So let me put this box somewhere here. Okay. Perfect. So should I start, Dr. Reddy?
Yes, sir.
Okay, so yeah, good morning to everybody. I'm very happy to be here, and I was reading about your institute and also about the university, Rajiv Gandhi University, and I was pleasantly surprised to see that it's a 6-year integrated course after the 10th class, and that was interesting information. So, Dr. Reddy, are there students of the university also you are sitting here right now, or only faculty colleagues from outside?
Yes, sir. For both students and the faculty are attending, sir.
Okay, from your university, or from also there are registrations from outside also?
Yes, sir. Registrations from outside, 30 people are there, sir.
Okay,
Meaning
let me welcome all of them. So let us continue the discussion which started in the morning. It was basically the focus of the previous speaker was on data centers and the optimization of let's say heat energy dissipation mechanisms and ways and means to dissipate the heat. Now what we are doing is also very similar. The heat flux levels are also pretty high there also and here also, depending on the situation. And I will be talking about development of novel cooling systems. There is some background noise. Can you mute everybody, please? Development of novel cooling systems for high power LEDs for enhanced reliability and lifetime. So as you have seen, many of you have seen that in our generation, in the last 10 years, the lighting which we see around us has drastically changed. When we grew up, we had incandescent bulbs, those yellow lights, which used to have an efficiency of the order of 2%, and as rest everything was heat. And then we moved on to tube lights, fluorescent lamps, CFLs, and now it's all LEDs. Okay, right from the automotive sector to street lighting to house lighting in household applications and in industrial lighting in large industrial plants. So now there are of course challenges. The efficiencies of LEDs are much higher than normal incandescent lamps, but nevertheless it also requires thermal management strategies. So welcome to this talk. Let us begin. So what we are going to do is, in this presentation, we are going to talk about high heat flux thermal management techniques for LEDs. I will also introduce you with the jet and spray impingement cooling. You have all studied and you know single phase heat transfer pretty well. Even in microchannels nowadays, most of the research in the last 20-25 years was there on microchannels. So you are aware of it, but as soon as you have a jet or a spray, there are two phases involved, and there is also the vapor phase which comes into picture. And therefore, the physics of the problem changes, and there are a lot of issues which come up because of the presence of the two phases. So we will be talking about water jet impingement cooling. We will talk about a little bit spray impingement cooling, which we are doing right now, both of these active cooling systems. Of course, as Dr. Reddy introduced me, I have been working on heat pipes, which are the passive systems. And somebody in the audience, they asked whether for mobile applications, can we have active systems? And the previous speaker told you that for mobile applications, you cannot have an active system because that requires a pump and a pumping system. But for stationary applications, you can go for active systems, and that is what we will be focusing on. The passive systems, typically heat pipes, for example, or thermosiphons, they are necessarily good for mobile applications, and therefore all your laptops, all your mobile phones, your electronics which moves around from here to there, that tries to put let us say passive systems like heat pipes, but in let's say standalone systems like computer centers, data centers, you can apply active systems, and this water jet and spray impingement are examples of active systems wherein an external pump is required. Now, why we have to go there? It is not an industry. Industry doesn't want active systems. They will be very happy with passive systems, but passive systems also have limitations. And if the heat flux is very, very high, then we have to go for such type of systems. We will see some design of the experimental setup and then see how we are proceeding in this project. This project, incidentally, started with collaboration between the Chinese from Xi'an Jiaotong University, who are manufacturing LEDs. Chinese are one of the leading manufacturers of LEDs in the world today. And they are now looking at very high power LEDs, which can go more than 500 watts per centimeter square, for example, also on the substrate level. The Russians were working on very high heat flux active cooling by liquid film cooling. And therefore, we started talking with each other. We met in some conferences, and then we started discussing whether we can do something together. And that's how the genesis of this project came about. And then we applied for the BRICS fellowship. Then we eventually, won the BRICS award, research award. And then that is how we are working together now. The Chinese are the LED manufacturers, and the Russians and the Indians, that is our team from India, we are giving the thermal solutions. So this chart is, of course, well known. I don't have to introduce this. This is the classic Moore's law, which tells you that it predicted the graph long back. That how the transistors are going to increase, and now, of course, the plateau is coming, and you have the previous speaker has talked about this plateau. But he has also said that the heat flux is increasing. So you can see this line here, and this heat flux is increasing very rapidly, and we are talking about 10 watts in computers. Now, if you see the failure rates of digital devices, you will see that the failure rate or the failure factor, becomes very high. It starts exponentially growing more or less after a temperature of about 70-75 degrees. So, a major portion of the failure of electronic devices is because of the temperature. So heat flux is one issue, and then with the flux, you have to maintain the temperature also. So you have to get rid of the net heat, net quantity of heat, and you have this extra constraint that the temperature should not go beyond about 70-75 degrees at the let's say the substrate level. At the junction level, it can go a little higher also, but then the clock speed, the frequencies, they decrease, and therefore you are constrained by this particular let's say a limitation. So what is true for electronic chips, this is microprocessors, is also true for other type of electronics, silicon-based electronics. And therein comes the LED part. So what are the thermal solutions? We have talked about some solutions. So I will just classify them here. So if you take an example of LED, for example, which is a light emitting diode, which we all know now. I don't have to introduce you to LEDs. What are LEDs? But they are very efficient luminaire systems. So you can have passive cooling, which like a heat sink or a vapor chamber or a phase change thermal storage devices or heat pipes, for example. So all that can be used here as a passive cooling. There is no pump required. And then if your operation is not met, or if your let's say aims and objectives are not being met by the passive cooling, and you have no other way but to go for active cooling system. Are you able to see my mouse, the movement of the mouse on the screen?
Yes, sir.
Okay, good. So so under active cooling, you can have microchannel cooling, you can have microjets, or you can have spray cooling, for example. So these are some of the standard techniques which we are. So now we are focusing on spray cooling. Spray cooling, of course, is well known in let's say metallurgy or in large systems. But how to miniaturize them, how to package them in an electronic component is what is let's say challenging. Now, in this also, you can have single-phase cooling or you can have two-phase cooling. For example, microchannel boiling you can do. Similarly, microjets can work in single-phase domain, and they can also be evaporating or boiling microjets. So depending on the saturation temperature and the pressure at which you are operating, you may have a system where the jet hits the hot object, and then there is vaporization also. So they become more complex, of course, as we go towards two-phase cooling, and some of the complexities we will see. So here you can see the diagrammatic representation. You can have a LED and you can put a simple heat sink, and that is what is usually done in standard standard LED modules. So at the end, I will show you some photographs, and you can put a heat sink here. Then you can also embed heat pipes in the heat sink. Okay, so here you can see embedded heat pipes, these orange colored regions, and then this will isothermalize at the sink level, and then you can dissipate the heat with air cooling, for example. You can also have a big vapor chamber here, and that is again a passive system. It is like a large heat pipe. It's also for isothermalization. Or somebody was asking about phase change materials. So you can also put some phase change materials here and absorb the latent heat so that the temperature remains constant in a certain period of time. But these are for intermittent operations, and you have to cool down again so that you get rid of the heat from the PCM. But the capacity of the system can be increased, and you can limit the temperature also. This can also act as a temperature limiter because it will start changing the phase at a particular saturation temperature. Now you can any of these heat sinks, you can actually put a fan and you can have active cooling. They can be natural convection cooled, or for example, on street lighting, you can have something like this with a natural convection cooled system. But if you have a larger light, you may require an air cooling or a fan at the back. And high power lighting may require a fan at the back, and this is what. So, for example, in stadiums, in the night when you have a day-night match, you have let's say large lamps, and they can be cooled by air cooling also at the back, or even liquid cooling. So these are the active systems. So as soon as you put a fan, you become active. You are no more a passive system, and therefore it requires external pumping power for thermal management. So here you can have a microchannel liquid flow which can be cooled in a condenser. The liquid can go in, and these are the microchannel heat sink, and the hot liquid can come out. And this again circuits. Then you can have a loop heat pipe. We are incidentally also working on development of loop heat pipes. So those who are interested, they can check my website, which I gave in the very first slide. So this is a loop heat pipe, and you can attach a loop heat pipe here, and then you can have single spray or a jet impingement cooling, which is also a very high heat flux management possibility. You can also have shear driven thin films here, which the Russians are working on, and then you can have multi spray or multi jet impingement cooling. So you can see the hardware structure remains, or the packaging structure remains broadly similar. You need a fan, you need a condenser, you need a support wherein you can attach your LED with your heat sink material, and then of course there is you have to talk about the coefficient of thermal expansion. You also have to take care of the thermal interface materials, TIMs, how to attach this LED with your heat sink. So these are some of the challenges, and you can see at the bottom that the heat transfer coefficient actually from natural convection, which is of the order of 10 to 15 watts per meter square Kelvin, it can go maximum of 50. You can also have a liquid pool here and get a natural convection by liquid cooling, but still passive. And then you can increase the heat transfer coefficient a bit. And then as soon as you have air cooling, you can increase it by 1 order of magnitude. And once you have a spray or a jet or a heat pipe, loop heat pipe, for example, with active cooling, then you can go to 2 or 3 orders of magnitude more. So you can see it can go from 10 watt per meter square Kelvin to all the way to 10 to the power 6 watt per meter square Kelvin as you change the technology. So of course, the decision of which technology to use depends on many factors, including techno-economic factors. But today we will not talk about economics, but the physics of these systems where jets and sprays are used for cooling. We have done a nice survey of all the possibilities and how to design these systems in this paper here, which has just published last week, in fact. And you can check on Applied Thermal Engineering this thing. So it is still an article in press. So you can search from my name and Applied Thermal Engineering, and you will see that a detailed review of technologies which are available for LED cooling and how to design them has been done by our group. And you can see here Dr. Gatapova, who is from Russia, Dr. Kabov, who is also our partner from Russia in the Russian Academy of Science in Siberia, and Dr. Hu and Zhao are our Chinese partners. So we have two partners from China, 2 partners from Russia, and Dr. Murlidhar and me are the partners from India, and Gopinath Sahu is a PhD student who is actually working on this particular problem. So this is the team now, and this, as I said, the funding has come from the BRICS, DST BRICS collaborative funding platform. So here you see the hardware. You can have heat sinks which LED attached. You can have a pool where you can keep it, liquid pool with again a passive system. You can have phase change PCM storage here. You can have micro channel photographs. You can see micro channels, and then we are working on micro jets and 2-phase spray cooling, which we will be talking about today. So when you go for, I will just quickly make an overview of what are the things we have done in the recent past. For example, can you see this video here? So this is a pulsating heat pipe, and are you able to hear me?
Yes, sir.
Okay, so this is a pulsating heat pipe which you just saw, and this we have been working from quite some time, and this is another device which can be used even for LED cooling. Of course, it has its own limitation. Here you see a loop heat pipe, a real loop heat pipe, which the Russians have developed. We have also done a lot of tests on such loop heat pipes, and we have now built our own loop heat pipe at IIT Kanpur. So these are passive systems. Then here you see a microchannel heatsink, which is like it's usually a conjugate problem, and then as the previous speaker was saying, you can attach the chip on the backside here, and there is Q which comes from this heater, which is the chip, and then you can take the heat out from these channels. There is an inlet port and an outlet port. So this was this study was done by my student Mohrana, Manoj Mohrana, who is now a faculty member at NIT Rourkela. So we started with active systems with microchannels, then we have moved on to passive systems with pulsating heat pipes and loop heat pipes, and now we are talking about sprays and jets as again an active solution. So here you see one of the videos which was done by my MTech student Naidu, Divakar Naidu. He also incidentally belongs to Telangana and Andhra Pradesh, the previous Andhra Pradesh, of course. And this we published in Interfacial Phenomena and Heat Transfer, and you can see this paper. And you can see here single phase cooling. Are you able to see the video, all of you?
Yes, sir.
Okay, good. So you can see a jet which is hitting. It's a few microns thick, and this is the hot surface. And the surface temperature is of the order of 40-45. You can maintain it, and you can see that the jet hits, and then there is a liquid thin film. The liquid goes in the radial direction outward, and you can see a hydraulic jump here, at the periphery. If you increase the heat flux, then boiling starts. You can see here boiling. Now you can see bubbles which are getting formed on the surface of the heater. Can you see the bubbles getting formed? And then you can see the explosions which are happening because of the bubbles. Yeah. And then if you increase the heat flux, so this is the nuclear boiling has started here, in fact. And this was single phase cooling, and now you have a convective cooling, and now you are moving on to a boiling type of a nuclear boiling type of a phenomena which occurs on the plate. And then if you really increase it, very high, then you can see a critical heat flux. Can you see CHF here? This is the CHF, and you can see the liquid jet is trying to hit the surface, but the heat flux is so high that you are not able to dissipate the heat at all. And you have reached the critical heat flux condition with this configuration, and now the cooling rate will drastically drop, and the surface temperature will increase very high, and you will not be able to take any heat out. So heat transfer is modest here. The heat transfer increases in nucleate boiling, and then when the CHF is arrived, the heat flux actually reduces. So these are videos which are taken by a high-speed camera in our laboratory of how the jet cooling, what is the hydrodynamics of jet cooling, and you can actually see the processes in front of you. So this is the increasing heat flux from low heat flux to high heat flux here, and the CHF has occurred at about 150 watts per meter square, and here it is about 15 watts. So there is one order of magnitude you can increase the heat flux, by changing the technology from single phase to two-phase nucleate boiling. Then you can do pool boiling also, which is another technology by which you can cool high heat flux electronics. So bubbles are formed, and it's like making tea. You give a lot of heat from this area. And then in microchannel, you can have bubbly flow, you can have slug flow, you can have annular flow or churn flow, and you can have fully developed annular flow, and the boiling patterns. So these are some of the complexities which come when you have two-phase systems, and the second phase also starts coming into play, and there are instabilities which get generated, and therefore you need to understand these instabilities and try to control them. So here I've just talked about the type of jet and spray impingement cooling, a state of the art, and you can see from the last 10 years or so, with two-phase spray cooling, you can really go to 1 kilowatt of that order. Our technique is right now we have hit about 400, but we are trying to increase this, and people have reached almost 1 kilowatt, of that order per centimeter square. So you can imagine how much heat comes from 1 centimeter. So 1 centimeter is like your thumbnail. You know, your thumbnail is of the order of 1 centimeter square, and you can imagine 1 kilowatt. 1 kilowatt of heat, of 400 watts, 900 watts coming from such type of systems. So this, if you use water, if you are able to use water with very high power jets, you can even go to 2 kilowatts of that order. Of course, these are technologies which are, some of them have been demonstrated in the laboratory, but they still have to hit the market. So that is what we are aiming at. So how to get rid of such type of heat fluxes from LEDs. Of course, LEDs have several advantages, and I will not go into the details. And we have already seen LEDs coming to our homes in the last 10 years in a big way. The government of India also promotes LEDs actively, and the energy efficiency of many establishments have increased quite a lot, because the lighting constitutes a large part of the energy bill, of a particular, let's say, building, enterprise, or an industry. And therefore, people are always looking for decreasing the lighting bill, and increasing the efficiency through material research. And we as thermal engineers, we work to get rid of the heat. So you can see the non-radiant heat energy is very high in an LED as compared to incandescent lamps. And therefore there are no incandescent lamps. If somebody uses them, we actually almost tell him to get rid of it, and don't use bulbs, because they are very poor, and use instead of bulbs, some LEDs. So many things are there. You can also make it smaller, but the more smaller you make, the more heat flux is generated, and that is where we come in as thermal engineers to get rid of it. So this is how an LED works. About 20% goes, 20 to 30% is light, and the rest has to be dissipated. So this is the junction where this semiconductor is. The diode is here, and this diode has a package. It has interconnects, and then there is a phosphor layer on the top of it, and the light, and most of it in the front portion is light. And then the heat which is generated here goes to the heat sink at the back, and here is where the management comes. So you can see it's a thermal resistance network from the chip to the chip mount to the mount itself, and then between the mount and the plug, and then the board, and then the heat sink, and then to the environment. So you can see there is a thermal path, and we have to facilitate the removal of heat from this point to the environment. And that is, so this is on the right, you see the actual package with many LEDs packaged together. This size is about 2 centimeter by 2 centimeter, so it's maximum 4 centimeters square. And this is the high power LED which the Chinese have developed, which they have given it to us for thermal management. So now let us have a quick discussion on the jet and spray impingement cooling. We go to the next section now. So here you see a typical jet, and I can just show you some of the videos which Gopinath has generated. So if the flow rate is very small, you can get intermittent flow like that, and this is very small mass flow rate, and you will actually end up with only drops of liquid, and then as you increase the flow rate, you will see that you get a proper jet, and you can see here the jet, the jet can wobble a bit because it is interacting with the environment with the shear interaction. And then as you increase so now you see the jet goes with a transition here. Okay, and first it is laminar, and then turbulent region comes in, and then finally you will have a spray type of a situation when droplets will form. So of course the Reynolds number is increasing, and depending on the Weber number of the system, you will see the flow. And here you see the jet characteristics. The jet falls on the surface, there is a thin film which gets formed, there is a hydraulic jump which occurs at the periphery, and you can see capillary waves on the surface, and there is a thin film here which takes away the heat. So now, of course, as you keep increasing the velocity, this jet will become into a spray. So first we will talk about the jets, and then we will talk about the sprays. Now, what are the parameters? There is a thin film which forms. That is an important parameter. The height is a parameter. The diameter of the jet is a parameter. The Reynolds number of the flow is a parameter. And then, of course, which liquid you are using at what pressure and temperature. So the inlet subcooling is also important. So these are some of the parameters through which we have to study the physics of how such a jet takes away the heat, and what are the guiding principles of optimization. Okay, so let us move ahead. Yes, so the physics is like this. We just saw these videos where you have a droplet flow, and then as you increase the flow rate, you have a long jet, and then the jet becomes unstable, and then after a while Rayleigh instability comes in, and the Rayleigh instability will again start making these droplets, and then the length, the free jet length reduces, and you can see that the breakup length, this is the breakup length. Okay, so that reduces again. So you start with some individual droplets. As you increase the flow rate, you become a jet, which there is a transition, and this transition again, you can see waviness on the surface of the jet, which is the starting point of the Rayleigh instability, and then it will break down into sprays. So if you have a very large Reynolds number, you will get a spray type of a droplet sprays here. Before that, it will be a jet. So this is how it works. So you have the formation of the hydraulic jump, and then you have this this flow which changes its direction. It is coming out from here and then changes its direction like this. So this is the stagnation point, and your material is here in this stagnation zone. And we are interested to find out the heat transfer coefficient along this jet. So this is, of course, a classical problem which has been solved analytically also. And depending on the configuration, you may also have an inclined jet. Sometimes in metallurgy, for example, if steel plates are coming and you want to cool them for heat treatment purposes, you can do a jet like this with water cooling. And where a steel plate is coming, this is also a classical problem in metallurgy and metal processing. So if you see the Nusselt number variation along this line, you will see that at the stagnation point you get the Nusselt number, and then this is the geometric center, and then as you go along, the Nusselt number reduces, and you get a distribution like this. So this is the physics by which the heat transfer takes place, and this thin film at a very high velocity going outwards is responsible for such type of a velocity boundary layer. There is a no slip boundary condition here and a free surface here, which if the vapor density is high, then you have to have an interaction here. Otherwise, you can have a free surface flow, which you can assume at this location. So how does this transition take place? Because we are interested to find out the spray also. So you can see first it is droplets, and then the droplets, the Rayleigh instability comes in. Then there is an onion-like a shape which comes here, and then these are the secondary. First there is a primary breakup, and then after the primary breakup there is a shear-induced breakup, because now the flow is accelerating, and the Weber number limit has been crossed. We are already in the unstable zone, and now the shear interaction between the liquid phase and the gas phase or the vapor phase is leading to deformation of the fluid particles, and then you will have a shear-induced breakup here, and then finally atomization will take place. So you will have individual individual droplets, which are now there is a droplet distribution, size distribution, and this size distribution is what we want to control through our process parameters, which is the Reynolds number and the jet diameter and the jet height and things like that. So let us see this transition. So initially you have a small pressure drop, and then the flow rate is small, and then as you increase the flow rate, you get you get this relay primary breakup starts, of the jet, and then if you increase the pressure drop, you will see that now the secondary breakup and the shear breakup has started. Okay, and then finally it will lead to atomization. Yeah, here. So you can see atomization is beginning now at a delta P of about 8 bar. So between 8 to 12 bar with water, you can expect typical fluids with a viscosity range. You can expect a nice spray. Of course, in IC engines, for example, the spray is at a much higher delta P. It goes on to almost like 40 or 30 or 40 bars or even higher, depending on the fluid and whether it is diesel or heavy oil and things like that. So many people have studied the sprays of fuels. Now we are trying to apply those sprays in a micro geometry and trying to package it for LED applications. So this is how. So we are interested to know the transition so that we ensure that if you want a spray of a certain droplet distribution, you should be able to get that with our process parameters. So these are some of the parameters by which you define your spray. So you have a nozzle arrangement. You have a swirling chamber usually to increase the turbulence of the liquid which is sprayed from the orifice, and you have a geometrical impact area of the spray. In reality, because of the shear interaction between the spray and the fluid around it, you may have a reduced area, actual impact area, and then this is your hot substrate or the LED which you want to cool. Now, depending on the type of nozzle, you can have the patterns. How does the spray pattern? What is the mass flow rate? So you can have a spray which is like a hollow cone. So there is very little mass coming in here. Most of the mass flow is in the periphery in this manner. You can have a sort of a flat spray or a flat jet, which has a mass flow distribution like this. You can also have elliptic type of a distribution with a mass flow distribution like this. And of course, ideally, you want the entire surface to have an equal mass flow rate, but that doesn't happen in reality. And therefore, depending on the shape of this orifice and the size of this orifice, you can control what type of a spray you want. Okay. So you can have light sprays with low mass fluxes, medium with high intermediate mass fluxes, and then very dense sprays. And when the spray impacts the surface, so let us look at how does it look like. So here you can see the spray is impacting a surface in slow motion. And now this is again a very interesting problem because you have so many droplets hitting the surface. Some of them are evaporating completely, some of them are evaporating partially depending on the temperature at which you are operating. And there is a lot of agitation which is happening on the surface of the heater or the chip. And you can see that it's a very complex physics which is also guided by statistical parameters of the spray. So it's not so easy to model this from a CFD type of a perspective after it hits the surface because you can see it is a very complex flow. The boundary layers are getting broken all the time, and then there is impingement which is taking place continuously. So you need to go for empirical, semi-empirical, or let's say scaling-based models, mostly in spray impingement cooling, and that is what you see in the literature also. So how does the heat transfer change now? So you can start with droplets which are impinging. So if you have a low mass flux, then these droplets will evaporate probably, and you will not have a film of liquid. But as soon as you change the boundary conditions, you will start looking at a film which you just saw, and then these droplets impinge on this film. Then if you increase the temperature further, then you may have film evaporation. So right now nucleation has not started because the nucleation requires a certain amount of delta T between the hot object and the fluid to start with, and therefore you will have evaporation. Then boiling may also start, as you have seen in the videos earlier, and then you will have dry spot formation at a still higher heat flux, and then finally you will have a film boiling or a crisis which will take place, which is shown here. So you can increase the heat transfer, heat flux to a certain extent. After that, there will be a reduction, and you are now in the film boiling regime. Therefore, you would not like to operate here. In fact, you want to operate in this region, that is region 2 mostly, and most of the devices are operating in region 2. And the heat transfer coefficient, of course, increases first and then decreases drastically once you have the CHF. So here you can see the order of magnitude of the heat transfer coefficient, which is very high, in fact, of the order of 8,000, of even 4,000 to 16,000, depending on what type of activities you are doing here. So what are the parameters of this spray? As I was telling you, there are three major things. The one is the nozzle geometry, that is the nozzle tip, what is the distance between this distance, the type of the nozzle which you are using. Are you using some also air, and mixing it here, or you are only using a brute force with a single liquid? The orientation of the nozzle, the diameter, and the shape. Then you have hydrodynamic characteristics, which is what is the volumetric flux, the droplet size distribution. Of course, they are related. So geometry is related to droplet size distribution also. It is related to volumetric flux. Then the cone angle also is related to the type of diameter you have, the flow rate you have. The pressure drop across the nozzle again depends on the geometry. So they are interdependent. And then again, after you hit the surface, you can see that the surface can be smooth, it can be rough or porous. It can also have different wettability conditions. So you can see here on highly non-wetting surface, the spray looks quite different after it hits the surface. Okay, so you can see individual droplets going out, and there is no liquid film now. So the physics changes. There is no film which is formed here on the hot surface, but there are droplets which are actually moving outwards. And then if you have some microstructure on it, depending on its wettability, there can be wetting or non-wetting. You can see here on this video here that how a non-wetting surface has been created where the liquid is not penetrating inside. Okay, it is actually in the fakir state. It is highly non-wetting. Okay, then you have porous material also can be there on the substrate, and then this can act as a capillary suction for this liquid which is dropping in. So it's a complex problem. You can see that it's a very rich physics and a lot of open parameters to control. So it is not so straightforward from a fundamental point of view. So now let us look at some hydrodynamics and heat transfer characteristics of such a spray impingement type of a cooling. So this is the type of setup which one setup which we have, and the other one which we are developing right now. So you can see here the heater. You can see the spray. This is a vacuum box which is controllable. Then there is optics. You can see the spray. You can light it, illuminate it. You have to put some pressure transducers, some temperature profiles, and then you need a condenser to maintain the pressure inside. So this is the secondary condenser or the primary condenser. And then you of course require a tank where the liquid will come in, or a pump, for example. And you also, if you want to mix, pressurize it with air, you can have a pressure. So this can go inside and make a spray. And then you need a control on this pressure. So you need some pressure controlling valves and flow meters. So this is, and then depending on this, what type of a pillared surface or another surface you want to make, that is what you will do here. And then the extra liquid will come down, the vapor will get condensed in this condenser, and then this will return back to our main chamber. And this main chamber is again a temperature controlled chamber wherein you can control the temperature. So you can either use this pump or you can use the pressurized tank, depending on what you are studying. And this is the heater assembly, which also you want to measure the thermocouples and temperature. So it's a construction which is here, the heater construction, and this is let's say important for measuring the surface temperatures, so that you can estimate the heat transfer coefficient as well as the flux which is going to the spray, which is going to this heater here. So some more details. We have characterized some nozzles from 800 microns to about 200 microns, so depending on this. So Gopinath, my PhD student, is working on different types of nozzles. We have to get the coefficient of discharge of these nozzles. You have to get the pressure drop, and we are operating between, let us say, 4 to 15 bar, of that order, so that we can get a jet as well as a spray. This, you can have a swirling plate on the top to increase the turbulence of the system, so as to increase the Nusselt number and the spray characteristics. Then you need to have some optical method by which you can see these particulates or droplets. And then you need an image analysis software, or you have to develop your own software to detect these droplets and get the statistical characteristics. So with different photographs which you get, you have to generate time-wise statistical parameters, and then depending on your resolution, you may have as the resolution increases, you can detect more and more smaller droplets, in fact. So we have a high-speed camera, and we use that camera and do a image J analysis, make a software to get the statistical parameters and of course the photographs will also give you the cone angle and the Sauter mean diameter, which is a good representation. So the volume divided by the area, gives an average value of the length scale, which is applicable for these sprays. So this is the way you characterize them. I will not go into the more details. The data is here. We measure the spray cone angle. We measure depending on what type of flow it is, the cone angle will increase, of course, with Reynolds number. And then as your Reynolds number increases, you will get smaller and smaller droplets, which are much more interesting for spray cooling. So you can see Sauter mean diameter decreasing with increasing Reynolds number. And then you can get the droplet size distribution. Here you can see, many different 12 and 15 bar in the next setup, because we still want the Sauter mean diameter to be still smaller than this. We have reached about 200 micron now, SMD, for applications. And then you get the droplet distribution, the number of droplets histogram as a function of droplet diameter. Naturally, if you increase the Reynolds number, the heat transfer coefficient increases, and you can see we have reached of the order of 15,000 kilowatt, 15,000 watts per meter square Kelvin, or about 15 to 16 kilowatt meter square Kelvin, with nozzle diameter of about 600 microns. And we also maintain the temperature at the inlet and increase the heat flux to about 40 watts per centimeter square at the moment. This is the type of data which we get from these tests. The nozzle height is not very important, although for packaging purposes we don't want this height to be too large. But we are talking about something like 5 to 20 millimeters, and you can see that the height doesn't make too much of a difference. Also the subcooling will be important, because the subcooling will tell you the maximum temperature to which. So the colder the liquid, the better it is, of course. But then there are limitations, because if you require too much of cooling other than what you can achieve in the ambient, so the industry will not prefer it. So the industry will prefer something which is at ambient temperature. So our inlet, the inlet has to be close to the ambient, but you can change the saturation temperature by changing the subcooling, and then you can operate your LED at different temperatures depending on the subcooling. So what we can summarize from these initial tests which we have done is that spray cooling can be used for thermal management of high power electronics. High-speed imaging and image processing is an effective tool for characterization. That is what we are using. And then, of course, the heat transfer increases with an increasing of coolant flow rate. We all know that Nusselt number is proportional to Reynolds. and that is what we are getting, and we can get easily with spray cooling of the order of 10 to 15 kilowatt per meter square Kelvin, is easily achievable at modest delta P's. The nozzle height is not very important, of course, depending on the H/D ratio of the nozzle, and then the subcooling can be controlled, and we can have thermal management at different temperatures with this methodology. So look at some actual results on LEDs. So these initial tests were on heaters, and now we move on to the actual LED. So this is the actual LED. You can see here it's voltage between 25 to 36 volts, and as I said, it is 20 mm by 20 mm. And there are small LEDs here. You can see the array of LED, which is shown here. So about 1 mm by 1 mm, more or less. And it can operate at about 300 watts nominal power. So every LED is 3 watt. And then you have 100 LEDs here in a matrix. Depending on, this center portion is the hotspot. And at the back, you have the substrate on which it is mounted. So this is a real LED. Okay, this is an actual LED. So basically, we have to model it on either ANSYS or COMSOL platform. Usually, we use one of these to model the entire system, and then we have to sort of see how it is manufactured, because we have to give the thermal conductivity and diffusivity values of the entire chip. So the Chinese have given us the construction material of this LED, so we can sort of construct the full model by putting in the proper values of these this construction, and this is what we need to model, and then do an experiment to validate whether the model is working or not. So we characterize the LEDs up to the point it breaks. You can see this after it is burnt. The layer on the top has now developed cracks. So we increase the current to a value very high, and then finally it breaks at a certain power. So you can see the nominal operation is 300 watt. So of this order, about 8 amperes. But if you keep on increasing, it will continue to work, but around 550 it will burn off. So the factor of safety is about 2. And therefore the nominal power is always 300 watt. Usually the manufacturer, as per the manufacturer, we should not go beyond 300 watts. So this is the construction. Now nearly 70% of the power is converted to heat. So if you are talking about 300 watts, then about 200 watts is heat, so which you have to take it out. Okay, the rest is all light and maybe some radiation which gets lost to the environment. Here we see we start the LED, let it come to a steady state, and then stop it, and then our model should be able to predict the initial transient here of the heating part, and then the achieving of the steady state, and then the cooling part. So that is what we have done. We have modeled this particular LED, and then try to do the characterization of this through the model and through the experiments. So there are different temperatures which we can measure on the LED module, and depending on the flow rate, you can get these actual values, and then you can see that the heat transfer coefficient is of the order of 14 to 15, depending on the flow rate, and of course the delta P. Then the effect of height, again you can see here the height doesn't make much of a difference. This is tests on actual LED. And then the radial distance, how do we keep this? So this also makes a little difference, but not much, because the size is small and our flow rates are pretty high. So this is also one result. And then of course, if you change the inlet water temperature, then the operating temperature will increase, and therefore we would like to typically hover around 20 to 30 degrees inlet temperature, because this is the atmospheric temperature typically. And we should maintain a temperature of 50 degrees, which is well below the maximum. So you can see that the jet and the spray are able to meet these conditions quite nicely. And then so after characterization of a single jet and after characterization of a single spray, we have now gone into multi-jet this thing, because in a real-time situation, the LED package can be pretty large. and therefore this will sort of we require multi-jets. So here is a module which we have now published with Gopinath Sahu and Gatapova, and along with our Chinese colleagues. We have published this very recently again in Applied Thermal Engineering. And here you can see that we made five holes, of about 400 micron. And then there is a chamber on the top here, and these 5 jets will come out. There is a central jet, and there are 4 jets which come out from the side. And this is the actual LED assembly, which we powered it with a DC light. So we actually did the complete characterization where the actual LED was tested. So the details can be found here. This is the setup. We require a high pressure pump, and then we make a spray and see the characteristics of this LED, whether we are able to maintain the requirements. Of course, there are thermocouples which are very closely fitted here on the top of this LED package, and the model, the complete console model should be able to predict this if the model is correct. So as you can see, if you start the LED, the temperature rises, and at certain point you start the spray, and suddenly the temperature drops and then comes to a steady state almost instantaneously. So you can see for about 105 seconds we started working, and now it is becoming critical. We are already, if we would not have started this spray, the temperature would have just shot and the LED would have burnt, okay, without any cooling. But then we had to start this at a safe temperature, and then we started it, and the temperature went down, and we get a steady state again with the spray of these 5 nozzles in the operating state. So here are the results. You can see that the nominal power is 300, and if you operate our multi-jet, we are still at about 40-45 degrees centigrade, which is pretty good, very reasonable. You can also increase the power, as I said, about 550 it got burnt, but after a certain while it becomes nonlinear because now the LEDs are, they are operating at high temperature, and therefore they are not stable anymore, and after a while they will break. So here somewhere there is a burnout. So you can see the surface temperatures which are well below the requirement. So even if you exceed the power by about 50 or 60 watts, you are still not bad. But after 400 watts, then the temperature really becomes 80 degrees or so, and then you are critical here. This is the average temperature, and this is the surface temperature which is obtained at the back. So at thermocouple locations TC1, TC2. So these are the TC1, TC2, TC3 thermocouples, and these are the data for that. And the average, of course, is the average of this plate. So here is the model. You solve the energy equation with generation term inside, and this is the standard equation. Of course, the boundary conditions have to be correctly given. On one side, you have the cooling, and the other, there is a heat spreader, and then there is a cooling here, and then this is our chip. And these are 100 such chips which are located on this substrate here, which is a copper substrate. So we get the die attached, the heat spreader, the alloy block. We put in all the values, and then we give the boundary conditions, which are volumetric heat generation. Then radiation is of course neglected because that most of the radiation is light, but of course there is other modes also, but they are within the limits of the uncertainties. So here you see the models prediction, experimental and numerical, and you can get a very good, let's say, if the model is good, if you are able to, let's say, get the chip dimensions correctly, all the material characteristics correctly, their thicknesses, we were able to do it because we are directly talking with the manufacturer. So therefore, collaboration with the industry is very important, because then you know exactly which material is there. Otherwise, you have to assume something here, and then that assumption leads to a lot of errors. So if you know exactly what you're doing, then I think this is a simple energy equation which cannot go wrong. So you can see experimental data and the simulation data here. This is the model predictions. You can see that after you start, the heat pipe, the LED becomes hot. Of course, the central portion is the hottest here, and then slowly the heat spreads out, and then you get a steady state. Okay, so this is how this is the cross section. At the bottom, you can see the cross section of the system, and then you can see the hotspot distribution within the LED module, and then from there you can get the temperature profile and the heat flux profile, and you can see it is already about 200 watts per centimeter square in the very center, in the central core. It's pretty high. Okay. So to summarize, water jet spray impingement cooling is very good. It's in fact we have tested it for 300 watts, even up to 600 watts. In fact, double the nominal power, and the temperatures can remain well within the limits. The numerical simulation is also effective tool for visualization as well as thermal characterization. So it is important that we learn this also, so that we can do a lot of numerical experiments and get the results. It is difficult to do a lot of experiments, so it is better that you validate the model and then try to get the best out of the combination of experiments and numerical work. The heat transfer rate increases, of course, with increasing coolant flow. The nozzle height is not very important. I've already told you. And the nozzle impingement vis-a-vis the LED is also an important parameter. So that's why we have to go. We cannot have only one spray, but we will have to finally go for a multi-spray type of a system. So to summarize, we have seen the basic physics of water jets, microjets, and micro sprays. And we have seen that they can be used for LED, but of course packaging is important, and we are not experts in packaging, but that is what we are learning now, and we will slowly move towards a good package, a closed circuit package for the LED. The heat, we have also learned in the process that the texturing of the surface of the LED is very important, and therefore the substrate can be textured and you can have very high heat transfer because of the texture. And of course, rugged and reliable packaging is the next task, and that is what we are going to do next. So let me say thank you first to all of you to have patiently listened to my talk. And of course, thanks are also due to my UG and PG students. And we are the Phase Change Thermal Systems Laboratory. I started this laboratory in 2004, and now 2020 is going on. So in 15 years, we could achieve some nice benchmarks. And of course, you are all welcome to come to Kanpur and join us and see what we are doing, and look at our website and get this thing. Some of the funding agencies through which we were able to, in fact, do these things is, of course, starting from IIT Kanpur to BARC to BRNS, ISRO, DRDO, Department of Science and Technology, BRICS, Indo-French. A lot of activity in our laboratory has also has an Indo-French connection. So the BRICS connection is between Russia, China, and India in our project. And then we just completed 2 projects with Indo-French collaboration, wherein we have developed loop heat pipes and pulsating heat pipes, also with industry collaboration. With ISRO, we have worked on pulsating heat pipes for space applications, for radiators, for example. And for BRNS and BARC, we do completely different things. That's to do with condensation heat transfer for nuclear reactor and safety applications. With DRDO, we have worked by giving them a solution for infrared camera, for thermal management with the heat pipes. And of course, the DST has been supporting us through various schemes, including BRICS, including for that matter, the CEFIPRA is also part of the larger network of DST. And then FIST grants, and in between some innovation and other grants which we have received from DRDO. And of course, INAE is something which we have started working with recently, as I was introduced by Dr. Konda. So thank you very much. I must also acknowledge here Vishwariya Fellowship, which is Government of India Fellowship, which my PhD student is availing right now. So this fellowship is especially for development of electronics and electronic components. He's getting this fellowship. It's a very nice fellowship. So some of you should also aim at getting this if you want to work in electronics and electronics management, including development of hardcore hardware for electronics. So thank you very much, and I appreciate your patience in listening to me, and I hope I've been able to give you a sort of a overview of what we are doing in terms of thermal management of LEDs. So thank you, Dr. Konda, and I am open to questions now.
Yes, sir. Thank you, sir. Now, participants, if you have questions, you can ask.
Hello.
Yeah.
Hello.
Please go ahead.
Hello. Good morning, sir. And its presentation was very nice, sir, and it was very informative. And I would like to thank you very much for this nice presentation, sir. And my question, now doubt is, what is the best method for LED thermal management? Best cooling method for LED thermal management?
Okay, there is nothing like best. Okay, for example, let me show you something here. Can you see this this LED light?
Yes, sir.
You see on my video?
Yes, sir. Yes, I can see, sir.
So this is a light which you can just put on a wall. Okay, and this is the light. Okay, I probably show you. Now, can you stop your audio? Stop your audio. So now you can see that this is a commercial product, and this is available in the market, let us say at 300, 400, 500 rupees. Okay, and it has an LED here. Okay, you can see the LED array. Can you see the LED array?
Yes,
Yeah.
sir.
Okay.
Yes,
So
sir.
now in this, if you have to sell this in the market, at 400 rupees or 500 rupees, you cannot have spray cooling, you cannot have jet cooling, you cannot have even a heat pipe, because nobody will buy it otherwise, because the cost will become 5,000 rupees. So are you ready to pay 5,000 rupees for this bulb for your office? So you will say, no, I will not buy it. Okay. So what it means is that now and then this bulb is now they have given some a casing on the top. So now the heat has to go from this casing to the environment. So there is nothing but they have done nothing excepting there is a natural convection connection between the LED and this module outside. So this looks like a nice design. It's more like aesthetics, but it is not aesthetics. This is a heat thermal management system, which is based on natural convection, and therefore there is no. It's a passive system. Okay. Now, naturally, you cannot increase the light here beyond a particular value, because if you do that, this LED will burn. Okay, but it is sufficient for a home, for a small lighting near the mirror. You can just put it. You can see the connection here at the back. I can just hang it from this point, and it can just go to the wall, and it can give me light on my table. Okay, small light. So for this particular application, natural convection is the only choice. There is nothing else you can do. Okay, if you want to increase the power a little bit, you can put some fins here. You can put some fins. So you can see on the street light, if you see a LED street light, you will see there are fins on it to increase the area. So you can either increase the area or increase the volume, or increase the heat transfer coefficient. Now, heat transfer coefficient increase means you are paying, there is some extra money which is involved. Okay. So whether it is really needed. So there is no single solution. It is not that, homeopathy is good or allopathy is good or Ayurveda is good. It depends on the patient. It depends on his condition. It depends on what type of solution the doctor is giving. It can be a combination, so you have to take a techno-economic decision and go ahead. So that is what my answer is.
So, hello, sir.
Yeah, please go ahead.
Sir, just my query in the fundamentals questions, the Renault number. Sir, how can define the Renault number for this spray and water jet case?
Right. So the Reynolds number is usually yeah, you mute yourself. Yeah. So the Reynolds number is usually defined on the diameter of the jet. Okay, so that is what is called as the inlet Reynolds number. Okay, so that inlet Reynolds number is where the liquid comes out of the orifice. Now at that point it is single phase. After that, then it can become a jet or it can become a spray, depending on, as I said, the transition and the flow velocity itself. So you will always define the Reynolds number based on the mass flow rate of the liquid, okay, into the density of the liquid, into the velocity of the liquid, and then the diameter of the jet, and divided by the mu. Okay, that is the viscosity of the fluid. Okay, so once it comes out, then depending on its inertia and the viscosity and the interaction with the surrounding fluid, which can be air or it can be the vapor of the same fluid, you will get disintegration into different, let's say, small diameter droplets. Now once that happens, then you usually work with what you call as the Weber number, because now the scaling is between the inertia and the surface tension. Okay, so you will start working on with Weber number. So in the Weber number, the velocity will also come and the diameter will also come, as part of your scaling. So that is, I hope that answers your question.
But sir, that suppose we have working in two phase, air and water are different density. Is 100
Yes.
times is the difference.
Yes.
So that Weber number is capture this phenomena.
Yes, because you can always use rho L minus rho G and get you can capture it. See, if the pressure is not very high, see, for example, in diesel engines, it is not so easy. It's not so straightforward, because the gas phase and the liquid phase, the gas phase is at a very high pressure. So the density of the gas is also very important. Similarly, you may have systems where we have two liquids in which the viscosity ratio is also very similar, mu1 upon mu2, for example. So in those systems, you have to deal with rho L minus rho G. Okay, that is one parameter which you can use rather than only rho liquid. Okay.
Okay, thank you, sir. Thank you.
Any other?
Any other questions from participants?
Okay, so now they probably are tired and they want a longer bio break.
Maybe, sir.
Yes.
Right. I would like to thank you, sir, for your excellent presentation on the development of naval cooling systems for high power LEDs for enhanced reliability and lifetime. Thank you, sir, for accepting our invitation and
thank you.
spending your valuable time with us.
Thank you. Thank you. Thank you. Thank you. So best of luck to all the participants, and stay safe. And it's a very good opportunity. You are at home. You can do a lot of reading. Okay, you're not wasting any time, but you can just do good work at home also. It is not, so make good use of your time and be patient, because now patience is going to help us in coming out of this pandemic. So thank you very much, and my best wishes and best regards to everybody, and have a nice time, and congratulations for arranging this particular workshop, Dr. Konda Reddy.
Yes.
Thank you very much. Bye-bye.
Thank you, sir.
Thank you.
Now it's 5 minutes of break for all the participants. Right now 11:47. 11:55 I will start the session. can take a break and you can be there, stay here itself, or you can join again back. No problem.
Dear participants, good afternoon one and all. I welcome you for the sixth session. For the sixth session, the speaker is Dr. B. Kondareddy. Before the session, let me introduce about the speaker. Dr. B. Kondareddy is currently working as assistant professor in the Department of Mechanical Engineering at IIIT RK Valley. He did his BTech in Mechanical Engineering from JNTU Hyderabad and MTech in Thermal Engineering from NIT Warangal. After MTech, he joined in General Electric as an addition engineer for 2 years. And in GE, he worked in the motor control center product line to replace the existing fuzzy motor drives with a new GE motor drives, during which he accomplished the design and analysis required for the product line. He left GE and joined a PhD in IIT Madras with an interest in research. He completed PhD in heat transfer from the Department of Mechanical Engineering, IIT Madras. He completed within 3 years. He published 7 international journal publications and attended 7 international conferences. He is a life member in Indian Society for Heat Transfer. He joined as a lecturer in 2013 in the Department of Mechanical Engineering at IIIT RK Valley and selected as assistant professor in 2013. He is teaching thermal engineering courses for UG students and doing research in the field of heat transfer, developing innovative products, and also handling administrative responsibilities. He published a patent on adaptable biomass cooking stove with movable combustion chambers and presently handling a MHRD project of design and development of biomass-fired wood gas stoves for rural applications. Now I request Dr. B. Kondareddy to start the session.
Thank you, sir. Now let me share my presentation. My presentation is visible to you?
Visible.
Yes, sir.
Okay. Yeah. Very good afternoon to one and all. First, I would like to introduce the topic, estimation of parameters. That means thermophysical properties in heat generating equipment using inverse heat transfer techniques. These are all the outline of the presentation. Introduction, parameter estimation in inverse heat transfer, in which I am going to discuss forward model, inverse model, measurement data, minimization of variance. Okay. After that, estimation methodology, Bayesian inference I will introduce, and then I will discuss liquid crystal thermography is a one of the temperature measuring technique that I will discuss. Based on all these inputs, parameter estimation methodology and experimental methodology, I'm going to solve. I solved 3 types of problems. Those problems how I did with using of inverse heat I am going to discuss. So after that, a grand overview of all I will review and then references. So the objective of this presentation is, as we have seen yesterday, Professor C. Balaji told, from the all electronic equipment at the surface of it, we will observe temperature distribution, right? From that temperature distribution, then he said we can introduce the inverse heat transfer, so that what are all the causes are making to get this temperature distribution. So we want what are all the causes. If there is a temperature distribution is working within the allowable limit of that particular product, it is well and good. There are no issues. Otherwise, if there is a hot spot is appearing over that temperature distribution, right? If there is a excess temperature we are observing, then what was the reason for that excess temperature? Either it may be a cooling is not sufficient, or whatever the design dimensions are not sufficient, or flow path is not correct. What are all the reasons? How what type of materials we used? And then we will inversely we can estimate those parameters, and then we will fix it, and then finally we will provide a good design for developing that product. So in this presentation I'm going to discuss inverse heat transfer methodology that will helpful for electronic cooling equipment. Right. Now, let me introduce what is a direct problem that generally we in our heat transfer in our coursework time there is any conduction, convection, radiation problem for a given set of input data parameters. Then we will calculate analytically or using some software, so we can find the temperature distribution. That is called direct problem. So identifying the effect from the known causes. Known causes are those are properties of the material, flow field for fluid, and then construction details of the problem, right? All these uh, causes which are known to us, it is given in the problem, and then finally we will calculate the effect, that is the temperature distribution. What is inverse problem? To identify the causes from the known effect. Okay, from the known effect in this sense, if we know the temperature distribution over the surface of the body or electronic component equipment, then we have to find what are all the causes involved for that problem. Yeah. In thermal sciences, effect is the temperature distribution, and causes are thermophysical properties of materials. Either it may be thermal conductivity, thermal diffusivity, specific heat, and emissivity, transport coefficient, heat transfer coefficient, and initial and boundary conditions also we can find. So those are all the causes, and the temperature distribution is the effect. Right. Then what is the problem in a direct problem and the inverse problem? Direct problem is a well-posed problem. It is we can from given parameters we can find the temperature distribution, that is the effect. But inverse problem, it is an ill-posed problem, because there are several causes can lead to the same effect. Suppose the causes are let us assume if we want to get 10 as a effect, what are all the causes? 2 plus 8 also it may give that same effect, or 5 plus 5 also it may give same effect of 10, or 9 plus 1 also it may give same effect of 10, right? So we do not know, that is the reason it is ill-posed problem. Okay, small changes in the effect can cause a lot of changes in the causes. If there is a small change in the effect, then there is a lot of change in the causes we will find. Yeah. Now let me introduce the uh, algorithm to there is a process of procedure to estimate the parameters using inverse technique. Yeah. First, let me go through this. We have to start with the initial guess parameter. Let us take some conductivity of K equal to 50 watt per meter Kelvin of the given material. Now, that thermal conductivity you want to estimate from the temperature distribution, right? So first you will introduce that K value into the forward model. Forward model is a mathematical model governing equation with initial and boundary conditions we will solve. We can solve either analytically or numerically using MATLAB, C programming, or using Fortran also we can use. And there is a software called ANSYS, Fluent, and COMSOL, such softwares, and ANN training. These are all the part of it in the forward model. In the forward model, we will solve the mathematical model of the problem, right? Whatever the physical problem we are writing in terms of mathematics, that problem we will solve for the given value of k. And then that it will come y simulated, that is the temperature distribution. From that forward model we will get from this is the direct problem. Then from measurement data, either you use thermocouples, liquid crystal thermography, or infrared thermography, any measurement technique we can use, and we will get a temperature distribution data. This measured temperature distribution data minus simulated temperature distribution data, if we make it as a square of it, then this is least squares regression. And then whatever the minimum value, if it is acceptable, then the value, whatever we have considered k value, that is correct. Otherwise, if I equal to n is nothing but number of samples. K equal to, you can start from 10 value, uh, 10, 11, 12, up to 15, up to 100. For now, you are introducing k of k equal to 10 into the forward model. You will get simulated data, and then your real data is from the experiment. That you will minimize that. Then whatever the error r square value is coming, that you will report it.
বিজয় কিন্তু মাইনে করে তো ওই জন্য বিনোদকে দেবো আমার কলেজের ছেলে অফিসিয়ালি সই করে তোমার যদি কিছু বলার থাকে মিউট করো নতুন প্রসেসটা নতুন স্কিমটাতে শুধুমাত্র এই বছরই সামনে বছর থেকে সবাইকে পুরনো বন্ধ তাহলে যাদের হাউস বিল্ডিং লোন আছে সেগুলো কনভার্ট হয়ে যাবে মরে যাবে সব এই মার্চ মাসে নতুন আবার দিয়ে চলে আসবে মরে যাবে হাউস বিল্ডিং লোন তুলে দিলে আর এবার আমি তো ট্যাক্স কিছু বেশি কাটিয়ে দিয়েছি এবারে ট্যাক্স কম হবে আগের বছর 1,80,000 দিয়েছি এবছর তার থেকে কম হবে এবার আমার অলরেডি 1,48,000 কাটানো হয়ে গেছে
Yeah, right. Thank you, sir. Right. Now, based on this sample which we are taking, then we will calculate the R square value, and then we will report it. And whichever the K value which will give Y simulation, that is the same as Y method, that R square value is the solution. So here, the next sample, either we can go next sample, it will be generated by inverse model. That is either we can use deterministic methods, either calculus based and search techniques, or stochastic methods, simulated annealing or genetic algorithm, or Bayesian inference we can use. Okay. The next sample it will be generated, and next sample it will given to the forward model. Again, this forward model it will be solved, and then we will calculate R square. Like this, until we are getting the correct solution, and this process it will be continued. This algorithm we will continue. Okay. Now in this inverse model, today I'm going to discuss Bayesian inference, which is the one of the reliability model we can use for finding the parameters. And here measurement data, I am using liquid crystal thermography for getting the temperature distribution. Right. Now, let us discuss what is a forward model. Forward models are mathematical models of physical problems represented as governing equations with a boundary or initial conditions. These can be solved using analytical or numerical methods for a guess sample of parameters depending upon whether they are linear or non-linear, and also on whether they are algebraic or a differential equation. Fine. The forward heat transfer problem is generally a well-posed problem. The solution of a problem should satisfy the condition of existence, uniqueness, and stability. What is an existence? It means that a solution is available for a sample of parameter. That is an existence of solution. What is the uniqueness of solution? Unique solution are that the same solution should be obtained every time the forward model is executed. What is the stability of solution? It is the solution must be stable even for small perturbations in the input. Okay. Then finally, accuracy of the simulated data depends on how the mathematical equation which we are constructing in the physical problem. Then the space and the time step independence study and validation of the mathematical model. These are all about the forward model. Uh, after a few minutes, after 5 to 10 minutes, I will enter into the really solved inverse problems so that you can understand completely that. Yeah. Now coming to the inverse model. Inverse models are parameter sample generating models that require repeated use of forward model to match measurements with the simulation. So here we are introducing a parameter repeatedly and solving the forward model, and then we are comparing with the measurement data. That is inverse model. Inverse problems can be solved using deterministic and stochastic techniques. Deterministic techniques can either be calculus based or search techniques. Yeah. Other point is gradient based techniques sometimes may end up with a local minimum or maximum, and if the function is not differentiable, the estimation is tedious. The efficiency of conventional search techniques is moderate across a spectrum of functions. Right. Some stochastic techniques that are frequently used are genetic algorithms and simulated annealing. Okay. About this, I am using Bayesian inference. It is yet another approach to solve inverse problem. The advantage of Bayesian inference is it can eminently handle the noise in the data. If there is a noise is present in the measurement data, that it can handle. That we can give in the input of the problem. Right. Another one is prior information about parameters. If there is a prior information about the parameter, either from literature or from your previous work experience, that input, that data also we can incorporate for solving this inverse problem. That is the advantage with Bayesian inference. That advantages which are not possible in the other cases of estimation processes. Furthermore, the Bayesian approach directly returns the standard deviation of the estimate. After estimating the parameter, how much standard deviation that with that we estimated also we can calculate using Bayesian inference. Now, there is a measurement data is required. With that measurement data, we have to compare our simulated data. Let me introduce. The measurement data required for estimating parameters can be obtained either using thermocouples. Traditionally, we do with thermocouples or infrared thermography or liquid crystal thermography. Using thermocouples, one can measure only at a limited number of locations. It is wherever the thermocouple bead location is there, that particular location only we can measure the temperature using thermocouples. But IR and LC thermography gives a temperature distribution over the desired surface field where more copious data is available for solving the inverse problems. So if we want to solve more inverse problem, we require more data. So more data we can get from the infrared thermography and liquid crystal thermography as compared with thermocouples. So thermocouple measurements is an intrusive technique. If the number of data points required for estimation increases, more thermocouples need to be introduced. In such cases, the geometry and flow and temperature field may be affected. That is the one disadvantage with thermocouples. But compared with thermocouples, IR thermography is a relatively reliable thermal imaging technique, but its application is somewhat limited due to high instrumentation cost. Coming to liquid crystal thermography is a optical, non-intrusive, inexpensive and quantitative technique for mapping surface temperature distribution. This liquid crystal thermography I used for my work that I will discuss later. Yeah, minimization of a variance. The these are all the points, whatever the forward model, inverse model, minimization of variance, and measurement data. These are all compulsory for estimating for any for solving any problem, any inverse heat transfer problem. Yeah. Now, the output of a forward model is simulated data, Y sim, and the output of experiments or measurement data, Y method. The objective function is to estimate a parameters at which the variance between measured and simulated data is minimum. Our objective function is forward model equation that we will get from the energy balance. For solving that objective function, we want to minimize this variance R square value, measured and simulated data. We have to, whichever the parameter, it will give the minimum R square value. That parameter is the correct parameter. Like that, we can estimate. Yeah. This is also called as least squares estimation, wherein if the sum of the squares of the differences between measured and simulated temperature at all locations is within the desired limit, the parameters are accepted. Otherwise, the next sample is generated from the inverse model and input into the forward model till convergence is reached. This is what inverse model will do, right? A simple least squares minimization was highlighted here, whatever the least squares regression. However, this has two limitations. One is inability to consider the uncertainty of measurement data. Here we cannot provide that uncertainty of measurement data, and inability to ingest prior information about the estimate. Whatever the parameter K, you may have some information, right, from the type of the material. Already people have done lot of work based on that literature. We can consider that data. That also we cannot incorporate into here. But in the Bayesian problem, Bayesian inference, we can introduce that. Yes. Now I'm introducing the estimation methodology, that is Bayesian inference. Thomas Bayes was 1701 to 1761. He was lived in England. He proposed this likelihood and posterior probability distribution function, right? So whatever the likelihood and posterior probability, they are directly proportional to each other. What is the likelihood and all, I will tell you. Once he has done, Bayes was introduced this Bayes theorem, and then after his death, his friend Price in 1763 he published. His friend was published this Bayes theorem. Bayes, he did not publish his work. Bayes theorem he did not publish, but based on his work, his friend Price was published. Yeah, what Bayes theorem states, which states that the posterior probability P of x given y, this is conditional probability P of x given y of an event is directly proportional to the likelihood density function P of y given x. Here x is nothing but a parameter. A parameter is nothing but it is either thermal conductivity or heat transfer coefficient or thermal diffusivity or any parameter, either initial condition or boundary condition which you want to estimate, whatever the parameter, that is x, and y is the measurement data, right? The likelihood density function P of y comma y given x, it is nothing but the relation between two conditional probabilities. These are conditional probability. Probability of y for a given x is proportional to probability of x for a given temperature with respect to heat transfer. This the Bayes theorem we can implement for other applications also, but our with coming to our heat transfer, we can imagine x is a parameter and y is the temperature distribution. Right. Now, the likelihood, yeah, for removing this directly proportionality, we can normalize it P of y. Then you can bring it to integration of P of y given x with respect to parameter dx integration. Right. The likelihood density function P of y given x for the measured and simulated data points is as follows. This is the equation likelihood. This is what are all the para parameters are present in this equation, there is a sigma. Sigma is a standard deviation of the measurement. If we are using thermocouple, what is the standard deviation of thermocouple? It may vary from zero point 0.1 to 1 degree C. Thermocouple standard deviation, when you are doing uh, comparison with a standard thermocouple, then that time you will come to know standard deviation of thermocouple is 0.1 or 0.2 degrees C, 0.3 degrees C, whatever. Where n is the number of data points of thermocouples we are taking, and then into e to the power of minus y measured minus y simulated. Y simulated we are getting from the forward model. T, this y measured we are getting from the experiment, and then standard deviation of measurement we are getting from this. Then for a given parameter x value, the probability of y from this likelihood we will get. That distribution and all I will show in the plots, so that you can easily understand that. Right. Now, now this likelihood density function and this posterior probability, these two are directly proportional to each other. Right. Now, there is a prior density function. Suppose this is a straight away, whatever this Bayes theorem first statement with the measurement data. Here, inference means educated knowledge. That educated knowledge in the sense we have to go to the field and we have to extract the data, and then based on that data only we will estimate the what are all the causes for that problem. Similarly, here also, uh, we went to the field in the heat transfer problem, and then we measured the temperature data points, and we are going to estimate the probability of x. But here one more thing is, there is multiplication of this likelihood with prior we are doing. This prior what we are doing, we will get it from literature. That value we can add up, so that the cumulative effect of this, it will give very good estimation. That is possible in the Bayesian inference only. Yeah. Now, how what is this prior density function? Let us see. It follows a uniform or a normal distribution. In the case of uniform prior, we will take p of x is 1. For in the case of normal distribution, normal prior, p of x follows a normal distribution with a mean value of mu p and a standard deviation of sigma p. The prior density function is the probability density of a prior belief or knowledge about the quantity x, even before measurements are made. Okay, before going to sample of parameter entered. Then like this, we will give number of iterations required, either 1,000 times, 1,000 samples. Let it generate until it is freezing, and then for each sample it will calculate posterior probability. If the sample is incorrect value, and when it enters into the forward model, automatically measured temperature from that it will be deviated, r square value it will increase, automatically probability will decrease, probability of that parameter it will decrease. So if the correct value of parameter, if it enters, r square value will decrease, probability of that parameter will increase, and then it will be printed at the bottom. Yeah, like this we can proceed. Now let me introduce the MH algorithm for single parameter estimation and two or more parameter estimation. Yes, in the MCMC based MH algorithm, first we are choosing one sample, first initial sample, that may be, as I said, correct value of K, let us assume 50 watt per meter Kelvin. You can start it from 30 watt per meter Kelvin, or 40 watt or 60 watt per meter Kelvin, or 70 watt per meter Kelvin. From there it will step by step it will reduce, and it will converge to the 50 watt per meter Kelvin. How? Let us see here. For I equal to 1, first sample it is entered, and we are generating a random number, right? And then we are calculating a next sample. This next sample is initially started parameter value plus or minus sigma 1. What is this sigma 1? It is a random number of into 5% of this first initial parameter, and then it may be plus or minus, randomly we will choose it, and then we will calculate x star. From this x star and xi we have to calculate acceptance, either it is correct value or not. How to calculate acceptance? Then there is a likelihood density ratio or proposal density ratio. For a given x star, you will find the probability, this likelihood, whatever the equation which I discussed previously, that equation we will use here for x star and xi, previous value and new generated value, this ratio multiplied with proposal density ratio. This proposal density ratio we will calculate like this, and whatever the proposed value it will enter into this equation with previous value, and we will calculate this proposal density. And for a given, for a calculated x star we are calculating, and then for a previous value of xi we are calculating like this, then this ratio multiplication of these two, it will come one value, minimum of 1 comma this calculated value, it will give the uh, x star. We have, then we will accept it, that accepted value is less than the random number which we generated, then that is a accept, then accept it, then it will go xi plus 1 equal to x star. Like that we will proceed, so that finally we will get the correct value of solution. This is for one parameter of estimation. If there are two parameter of estimation, let us initialize first parameter initial value and second parameter initial value, these two parameters. Then we have to generate the next samples. First, if you we generate a random number, with that random number we will compare with the acceptance value, and then if it is accepted, acceptance value in this sense, this procedure it has to do the program, likelihood density ratio and proposal density ratio, it is a part of it, and then we will come to know acceptance value. Once it is accepted, then xji plus 1 equal to xji, and then else go to the step 2 with previous value. Like this, the next sample generation we can do in the online Bayesian. This is what we can observe here. Right now, until here, I discussed whatever the inverse heat transfer problem for solving the for finding the parameter estimation, there is a procedure in which we have to solve a forward model, and then we required inverse methodology, and then we required measurement data. Yes, now we are coming to the measurement data. We can in heat transfer or for thermal sciences, generally we use thermocouples. Apart thermocouples, there are other techniques like infrared thermography or liquid crystal thermography we can use for measuring the temperatures. Yes, here what I did, liquid crystal thermography here I used for getting more temperature distribution. Right. The experimental setup we can construct like this. Test setup we can provide here. Over the surface of that test setup, we can paste a liquid crystal sheet, and then this when the temperature of this test setup is increasing, the color of the liquid crystal sheet it will change. That color change we will capture with the a camera, and then we will record it. First, we will calibrate the colors into temperature, and then that temperature we use for estimation process. Right. We can observe here the temperature distribution. Here, this is the fin assembly. There is a camera, illumination system, lighting system, dark enclosure we can use, data logger, DC power source, and a computer. This is the test setup is required. Yes. Now, liquid crystal thermography is an optical, non-intrusive, inexpensive, and quantitative technique for mapping surface temperature distribution. Yes, applications we can see in basic heat transfer studies, flow visualization, electronic thermal management, and medical diagnostic. So, from this experimental setup, straight away we don't get any temperature values. It will give colors. That colors we have to convert into in terms of a hue value, hue, saturation, and intensity (HSI), in which hue only we will calibrate with respect to the temperature of thermocouple. First calibrate, we will calibrate, and then we will attach it to the test setup. Right. Now, this is the first problem I am going to discuss now. As of now, I introduced the inverse heat transfer process, which required all the estimation methodology, measurement information, and forward model, inverse model, all the details I discussed. Now, let us see a simple problem. Experimental setup, it is like this. There is a fin of mild steel, made of mild steel, with 250 length and 150 length, and a thickness of 4 and at the base we are giving heat supply. When heat is from the base to tip, when it is going, the temperature change we can observe along the length of the fin. Yes, this is the way we can observe here. And this temperature, if we convert into this color, if we convert into temperature, we will get the temperature distribution like this. This is the base temperature, and this is the tip temperature we can observe. Yes. Now, what is the forward model for this fin problem? This is from the energy balance equation. We can derive this governing equation, and then we will get d square theta by dx square minus hp by ksa, in which we are assuming h is varying temperature heat transfer coefficient with respect to the temperature along the length of the fin, that we are incorporated. Now this is a total is an objective function, right? This objective function with the boundary conditions, and we are solving with a numerical model, finite difference Gauss Seidel iterative method, and a grid independent study we have done. 31 data points are required along the length of the fin, and we can validate this forward model with our analytical solution for a fin problem. That is easy. Yeah. Coming to inverse model, instead of that, whatever I discussed Bayesian inference, for this problem I did not use that. I used only simple golden section search method. It is a search method in which the minimum value and maximum value, lower bound and upper bound we are fixing like this. lower bound and upper bound. From this, every step we will reduce this much quantity of space we can reduce, and then this is the your region of solution. Again, you will reduce this much. Like this, you can solve this model, and every time one x value it will be introduced, and then it will be solved, and you will get the final solution. Yeah. First, what I did. For a instead of doing getting measurement data, there is another simple way of doing is getting surrogate data. What is surrogate data? It is a simulated data we are getting. For that simulated data, we can introduce some noise to the simulated data. Then it will become a surrogated data. We assume that this surrogate data as the same as the TLC or measured data, right? Based on this data and for assumed value of zero point 0.8 and 1.2 and base temperature of 50 and ambient temperature of 30 for the fin problem, and this is 0% noise, and with 3% noise we can estimate. If there is a 0% noise, as it is we will get 0.8, 1.2, whatever you are assuming feeding to the uh, uh, forward model, that you are getting as it is. If we are giving a noise, 3% noise, then automatically instead of zero point 0.8 you are getting 0.84. With that, the percentage error in parameter estimate 6.15, like this we will get. Okay, this is we are validating with surrogate data, but we conducted experiment and we have a TLC data. And TLC data based, we are giving 8.16 watt, 9.27 watts, like this. There are 8 experimental test setups we have conducted. Along that temperature length we have taken and we estimated. So in the first experiment we got a value is 0.91. In the next experiment 0.97, 1.04, 0.95, 0.92, 1.05. Like this we are getting, and average of it is 0.98 with a standard deviation of 0.07. We can calculate based on this data. So now our parameter of A, this is A, this is the unknown which we considered in this problem. This A value, this A value, if we are able to calculate, uh, then our job is we can calculate the nasal heat transfer coefficient. After calculating based on this A value, then along the length of the fin, this is the length of the fin, you can calculate the heat transfer coefficient. We can calculate for various power levels. It will be like this we will get. Now this is uh, now after getting this parameter, and if we are solving again the forward model, we will get a temperature distribution. That temperature distribution, if we compare with the simulated temperature, it is 2.5%, uh, uh, 2 it is aligning with the experimental data. After getting this parameter from the solution, based on that solution, if we again calculate it, is experimental data and the simulated data, they are matching each other. The error is 2.5%. We can observe in this parity plot. Now let us take another problem. Here, the another problem is another heat sink fin. We can take, there is a base here, heat generation it will do, and this is the fin we can take. The temperature distribution can do for solving numerical method forward model or problems. Yeah. Now inverse model offline Bayesian we can use as well as the online Bayesian also. I used it. Now let us see here. So we want to generate the next sample now that will be introduced into this forward model, and then we will calculate posterior probability. Yes. Here in this problem, I am generating some prior information about heat transfer coefficient at a steady state, right? If we observe heat transfer for a distributed system at a particular given temperature, we can observe there is a rise in temperature, transient, this we will call it as a transient heating of a object, and then once if we switch off the power supply, then transient cooling it will be happen. Now, what we are doing at the steady state, we are getting heat transfer coefficient, and then that heat transfer coefficient is the information prior in the transient heating to estimate heat transfer coefficient as well as thermal during transient heating and during transient cooling. So that is second parameter, and the first parameter information we are introducing here, and we are calculating simultaneous estimation of heat transfer coefficient and thermal diffusivity during transient heating as well as transient cooling. So as I said, likelihood alone, it is a widespread standard deviation we will observe. With the presence of this prior information, the estimate of the parameter, we will get correct value as well as the standard deviation, it will reduce as compared with this likelihood alone. Yeah. Now let us see these. There are samples offline, online Bayesian we implemented for various base temperature. This is surrogated data. Surrogated data is nothing but just for a given samples for forward model. You run forward model. You will get a temperature distribution, simulated temperature distribution. For that simulated temperature distribution, you add some noise, either 0.1% to 2% we can add. Uh, by adding noise of that temperature, and then we will assume that that is a measured data. That measured data is same as the surrogated data. For that case, for base temperature of 60 and 80, and assumed value of a zero point 0.7 and alpha thermal diffusivity for these two values, then we can estimate the sigma 0% noise along the length of the pin for various power levels, then we will get like this temperature distribution. And the whatever the TLC data, and after estimating that parameter if we introduce in the forward model and we are getting the temperature distribution for various power levels, then if we see the relation between estimated parameter temperature distribution and the actual temperature of a TLC, then there is a well correlated, both are well correlated, plus or minus 2% error is there. So based on this, whatever the parameter we estimated, H theta and alpha, uh, they are well and good. That is what we can observe here. Yeah. Next, the third problem here, estimation of QS and alpha in a Teflon block. Yes, this Teflon block we can see here. There is a heat generating ball we are constructed like this. There is a aluminum heater. This is a nichrome wire we winded, and then we are giving power supply. It will generate a heat, and this heat it will be dissipated to this Teflon block. From this Teflon block, it will go to the ambient. So when we are conducting the experiment at the front surface of this Teflon block, it will be appeared color like this in the TLC sheet. If there is no TLC sheet, it will appear as it is white color only. But as an instrument we used as a TLC, then we will get a color distribution like this. For this color distribution, if we convert into in terms of temperature distribution, then we will get like this over this front surface. Based on this temperature data, we want to estimate what is the power supply we are giving to the heater, and then thermal diffusivity of this Teflon block, how it is during transient heating and transient cooling, how it is be thermal diffusivity value it is giving, that also we can calculate. Now let us see. Forward model is, this is a three-dimensional steady state problem. Also we can use a transient problem, and then we are giving initial and boundary condition, and we are solving in the fluent. Fluent, we can construct a geometrical model, and then we are giving all the options, inputs like boundary conditions, material type, and then finally we are going to the solver and then solving. Right, we will get a temperature distribution. All these things, inputs we can use, and then once getting that temperature distribution, that is every time for every parameter enter into the forward model, we cannot give straight away from the fluent to inverse model. So what we are doing, for some set of data points, some inputs of parameters, and we will get some temperature distribution. We are correlating with ANN, artificial neural network. For certain QS value and alpha values, we are getting temperature value that we are correlating. That equation we are using in the inverse model for estimating the parameters. Like that we can do. Yeah, this is estimation with the TLC data. Straight away I'm implementing here in this problem TLC data and estimating parameter. Here for A value we require 2000 samples, alpha value 2000 samples. If we are simultaneously estimating A and alpha, then 10,000 samples are required for running the online Bayesian. Right. Now, estimation of QS using online Bayesian from steady state TLC data. Okay, for a steady state, at the steady state, we are estimating QS value, single parameter estimation. So we are getting this is the actual input of value we are giving to the heater, and we are measuring in the, we are seeing in the power source, DC power source, and from the estimation we are getting this. What is the percentage of unaccounted heat loss? We can observe 2.12% heat loss. It is unaccounted. We can observe like whatever the estimated value for respective powers we can show here is the mean value, and it's a standard deviation also we can observe it here. Right. Yeah. Similarly, for online Bayesian, for single parameter of alpha, right, during transient cooling, then whatever the uh, power levels we heated up and then we stopped it, that power level we are taking it here, and then estimated value of alpha we are getting it here, and then it's a standard deviation we can observe it here, right? Estimation with the TLC data. So online Bayesian I use, transient heating I'm using here, in which both alpha and QS I'm estimating. QS without prior information and with prior information I'm giving, and then the respective reduction in the standard deviation we can observe it here. Uh, this is the reduction in the standard deviation. We can observe it here. Similarly, for estimating alpha also, right? These are the values we will get. Yeah. If we see the plots, estimation of QS and alpha simultaneously for without prior A and C. This is the without prior A and C. And with prior, these two are the posterior probability distribution, marginal PPDFs, because these are two parameters with the transient heating TLC data at 3457 watt per meter square heat flux. For that case, I have mentioned. And then here estimation with the TLC data uh, for a QS, from the estimated QS alone, we check the TLC temperature and simulated temperature. If we plot it, the parity plot, we will observe 5% plus or minus 5% error for all these experiments. And this is a alpha value, estimated alpha value for all these power levels of experiment. If we observe plus or minus 5% parity plot error, we can observe. If, if it is a two parameter estimation simultaneously, then for all experiments, QS and alpha value, and we will introduce in the forward model, and we will get simulated data, and TLC data we can straight away we will get, and if we compare between these two, we will observe plus or minus 10% error here, right? So this is a grand overview. Here it is, it may not be visible, either it is visible or not, I don't know. But whatever the three problems I discussed, in the grand overview I mentioned, the procedure using inverse heat transfer for solving a problem and getting an estimated parameter, this procedure we have to follow for any problem we can take, especially in electronic equipment. If there is a temperature distribution we are getting, if it is within the allowable operating limits, there is no issue. If it is going higher, then what was the reason behind that overheated? If we want to know, you can model as a forward model, mathematical model, and solve it, and then where it is coming higher temperatures, we can observe it, and then you can tell, you can define that estimated parameters. These are the references for my research work I have done. Thank you. And now questions from participants you can ask. I would like to share feedback form now. Please hold on. Uh, Outbox where- session 4 feedback form. This is you can give, and this is session 5 feedback form.